Muy buenos días. Good morning to everyone here and remotely. I extend a very cordial welcome to CICESE this morning. We are here convened by a very significant group of people that have been working on the improvement of connectivity between the academic and research networks of the United States and Mexico for quite a long time. Gradually, connectivity is improving. Reality is finally catching up with us. We today have a large capacity connectivity, especially between Baja California and California in the United States, that will allow a much better scientific collaboration between Mexico and the United States. Thanks to the idea of Professor Larry Smarr to convene a workshop between scientists in Mexico and in the United States that could use these larger capacity networks. We are here together. I would like to especially thank Julio Ibarra from AmLight and Luis Fox from CINIC for making this possible. And also would like to thank our hosts here, CICESE, Federico Graf, it's a Director General, for hosting us and for providing opportunities to participate and to follow up on the very important opportunities that are highlighted by the many participants that we have in the workshop. I would like to ask Federico to provide welcoming messages to all. He has the representation of the head of Mexico's CONACYT for this event. Please, Federico.
Good morning, everyone. Good morning. Well, on behalf of Dr. Enrique Cabrero Mendoza, who is the General Director of CONACYT. CONACYT is the National Council for Science and Technology of Mexico, and myself as Director General of CICESE, I would like to welcome all of you to this important meeting concerning the subject of big data and big networks. Looking back, I can't avoid feeling amazed at the road that we have traveled. I remember that in 1982, the Commodore 64 was launched. It was an 8-bit home computer with only 64 KB of RAM. Now we have achieved the capacity to manage an amount of data that exceeds the wildest dreams of the information pioneers. Our language is now full of terms such as petabytes, exabytes, and data sets. Just to highlight the reference of the topic that we will be discussing in this meeting, Smart Cities Will Need Big Data is the title of an article of the Physics Today, September 2013 issue. What are we doing in Mexico? Well, we're happy to report that the new federal government has increased the budget for science and technology around 11.5%. Compared to the previous fiscal year, and we are expecting even a higher increase from this year to the next. CONACYT will get a 20.5% increase in its fiscal budget. This increment is being distributed among CONACYT or through CONACYT. And as an example, I can mention the 34 million pesos that were assigned to the Red NIVA that connects all centers of CONACYT and universities in Mexico with the collaboration of CUDI. Carlos Casasus knows about this, through a joint effort with the Ministry of Communication and Transportations. That budget has allowed a huge increment in interconnectivity for research centers like CICESE of up to 10 gigs. The Big Data, Big Network meeting was organized with the ultimate goal of creating cross-border projects, using the AmLite West Link and creating new networks of collaboration. This link represents a new way of doing science because it creates new networks of collaboration between researchers and students that will let them devise solutions to problems that affect our lives as a nation and for humanity at large. I would like to end by acknowledging and recognizing to all those that have participated in organizing this meeting. I would like to thank all of you and the people that are not from CICESE, people abroad, the organizers, Julio Ibarra, thanks, and everyone in your staff, CUDI, and of course the people here at CICESE that has made this meeting possible. Thank you very much.
Great. Good morning. I'm Julio Ibarra, and thank you for being here. And it's great to visit CICESE. I understand that this is a special period for CICESE, so it's great to be able to have this meeting here and come together to talk about this big data and big networking collaboration that we've been working on for, I think, almost a year now, since we started this conversation about bringing together this special group of people. So I'd like to give a brief introduction about the workshop and what led to what we're doing here. So I'm going to be brief about this and just help get us started. So first, I'd like to give a little bit of background about the AmLite project. The AmLite project is what's called the International Research Networks Connection Program. It's a project under that program of the National Science Foundation, and it's the project that provides connectivity between USA, the United States of America, and Latin America. And this is a project that aims to enhance research and education in the America and is primarily operating international network connections with the different operators and collaborating organizations within the Americas. In particular, we have the 10 gigabit link network connection between California and Mexico called AmLite West. And that's going to be the focus of one of the workshop and one of the reasons we're talking about the collaborations between Mexico and California and the U.S. And the project also engages the U.S. and Western Hemisphere science and engineering research communities, and it creates an open instrument for collaboration. Those are some of the basic goals of what the AmLite project focuses on. The collaborating organizations that are involved with AmLite, you see here a list of a number of institutions. Florida International University is where the award is based. I am the principal investigator. Scenic is a collaborating organization. They operate the connection between California and Mexico in collaboration with CUDI. And we have a number of other organizations for the connections that go to different parts of Latin America. For example, we have organizations from Brazil that are also participating in the projects and cooperate the circuits between the U.S. and Brazil. Now, between the U.S. and Mexico, we have the 10 gigabit link, and it has connections in Los Angeles, San Diego, Tijuana, and Ensenada. It's operated by CNIC, CUDI, and CISESE, and was officially unveiled in May of 2012. One of the main applications that aims to use the connection is the Octubre. This has been a long collaboration between CISESE and CalIT2, and we work closely with Larry Smolar and members of his team in describing that application in the proposal for the project. And it also provides enhanced network resources for the local campuses here, such as the UNAM and the UABC. These are objectives or how we came to be able to get the support that we needed to get the link established with funding from the National Science Foundation and also from Mexico. Now, some of the background for the workshop is once the link was established, we were the stakeholders of the collaboration, which is the AmLab project, CNIC, CalIT2, CUDI, and CISESE. We began to discuss how we can enhance this cross-border collaboration using the 10 gigabit link. We have a lot of capacity available there, and we want to be able to bring in more users, more scientists and students to be able to create new ways of collaborating between the U.S. and Mexico. So the outcome of, we had a meeting last year at the CNIC conference, and one of the outcomes of that meeting was to organize this workshop. And we established a program committee, and the result was to organize it under the context of big data and big networks. And we invited scientists. You are here. A number of them are remotely participating. We have network operators from CNIC, CUDI, AmLite, CalIT2, and CISESE. And together, the objective is for us to have discussion and learn how we can explore new ways of forming what these cross-border networks of collaborations. So I wanted to describe here, and specifically the objectives of the workshop, is to inform the stakeholders on what to focus on. We want to know how you see the current environment and how we can increase use of this 10 gigabit link. As scientists and users, it would be, it's part of what we need to know to help us start to work in a way to better support the user community. We want to be able to inform scientists on new ways in which to conduct network-enabled cross-border collaborative research, and also inform the funding agency and provide them with recommendations towards investments in network infrastructure, and also provide more support for cross-border science research and education collaborations. In the work that the panel did, we came up with these themes, or not the panel, the program committee for the workshop. We came up with these themes of areas that there are existing collaborations or potential for establishing new ones. And so we have speakers that will be on panels for each of these different themes here throughout today and tomorrow. And there's some questions that we've asked the speakers to address on their applications and how they can help us, provide us with information as to how we can increase the collaborations between the cross-border collaborations through the use of the network. So we would like for the speakers to reflect on this. I hope that you've had enough time to incorporate this into your presentations and provide us with feedback. And from this is where we'll start to get a better understanding of what specific actions to take to improve the cross-border collaborations. There will be a report. We have a report writing committee that will convene on Friday after the workshop, and there are members from each of the collaborating organizations or the stakeholders on the committee, and the idea is for this report will go to the National Science Foundation and to the funding agencies here in Mexico, and it's basically to serve as an instrument to start to help all of the stakeholders be able to move forward. Today it's in the context of the AmLite project. Tomorrow it may be in a different context, but at least it'll provide a roadmap is the intention. And if anybody would like to volunteer to be on the report writing committee, please see me. You know, we have good participation, but if we welcome others to participate as well. This is a workshop, and the intention is to work together and get some work, be productive the next day and a half, and move forward with this. So thank you for your participation, and we can go ahead and start to get to work here. And the first order of business to do that is I will introduce my good friend Tom DeFonte. Let's see here how I do this. So let me just introduce Tom here a second. So Tom DeFonte is a research scientist at the Qualcomm Institute. Let me do it this way, because otherwise I can't read this. He is a research scientist at the Qualcomm Institute, a division of the California Institute of Telecommunications and Information Technology, University of California, San Diego, and a distinguished professor emeritus of computer science at the University of Illinois, Chicago. He is principal investigator of the NSF IRNC program Translite Starlight Project. He is recipient of the 1988 ACM Outstanding Contribution Award and was appointed an ACM Fellow in 1994. He shares recognition with fellow UIC Professor Emeritus Daniel J. Sandin for conceiving the Cave Virtual Reality Theater in 1991. And with that, I'd like to welcome Tom to give the keynote address this morning to the plenary here. Thank you, Tom. Yeah. Oh, button. Thank you. And to the PowerPoints. There we go. Good morning. Could we turn the house lights down a little bit? I have very colorful pictures, so. Good. Thank you. So I'm here. Larry Smarr was originally going to give the keynote. Larry and I and Greg Hidley and Maxine Brown came here, and it seems like 10 years ago, to kind of start this connection process. And so we're very happy. I'm very happy to be here to represent myself and Larry, and Greg is here, and Maxine is always in the network somewhere running everything for us. So originally, I entitled this presentation, Big Displays for Big Data Served by Big Networks, right? And 10G networks, but UCSD in particular and throughout the United States are very quickly pushing towards 40 and 100G networks. But last night, and where did he go? Where's Dave Reese? Did he actually, he's on a conference call. So last night, we were talking to Dave Reese, and he got into this conversation. Dave is a very funny person,
But he was talking about something serious. He talked about how he'd injured his big toe. But he explained to us that doctors call it their great toe. It's not the big toe, it's the great toe. So I decided I would rename my lecture to Great Displays for Great Data Served by Great Networks, just for today. I'm not going to change the National Science Foundation. But I actually think I was thinking about this a lot, because when we think about big data, I think what most people talk about is not large data or, huge amounts of carefully curated data. They're talking about stuff that's just out there that has probably just about no meaning to it, and the exercise is really to go comb through it and to figure out, whether your daughter is pregnant by the stuff she's ordering online, or, whether you're, going to buy Pepsi next week and they should send you a coupon. That's big data, right? Now, I don't think we do big data. I think we do great data. Right? So I want to think about this as different. And we do have great networks, and we have great displays. They're big displays too, but, so are billboards, so we do great displays. So with that, I'll go on to, now these are Larry's slides that I am doing for the first part of this. We've been watching since we opened Cal IT 2 in 2005, the cost of ports for 10 gig networks go down from about $80,000 a port to nowadays where the ports cost about the same as the graphics cards, in the computers. So this means that if it costs the same as a graphics card, this means that 10 gig networks are gamer tech, right? That's what people would buy for their homes, for their video games, if they could, right? And it would be probably getting down to the price of what people are willing to spend for video games. I think that scientists ought to at least have as good equipment as video gamers have. So this is a good price point. I used to tell my students that when computers cost less than 3-year-old used cars, the world was going to change. That was a long time ago, right? So now 10 gig networks are getting to that point, especially on campuses. So if you look at the switch we just bought, it has 576 ports on it, and it costs about $400 a port. The fiber costs more. So this is good. This is good. So this is the Arista switch, and this one is at San Diego Supercomputer Center, and I don't know how much Nancy's going to talk about any of this. None of it? Good. Okay. So it allows all of these computers, the Tritons, the Trestles, the cloud storage, and Gordon supercomputer to connect together with huge numbers, 128 10 gig links. That's, a teralink, right? I mean, that's a terabit link. And this allows us to go also into the parallel file systems. I mean, this is what we dreamed about for years, is these systems that essentially don't have bottlenecks in them, that can provide access to huge quality data. And Gordon, because of its structure of being built out of flash memory, has beat all sorts of records in I/O, and also inspired a new generation of computer systems I'll talk about in a few minutes. Now, we have been working with CNIC on the 100G campus connection to terminate that and to make meaningful use. Any of you who know me know that we've been doing 10 gig point-to-point experiments for a long time now, for 10 years, through Chicago, Starlight, through Amsterdam, through CNIC in California, to San Diego, to Japan, to all over Europe and other places, South America. But these have been mainly experiments that have been set up for a little while to work through the technology, to see what part of the system's a bottleneck, what part breaks, how to make it work well. with the idea that we would be able to use use this knowledge to have more systems in the future. The problem is when you have a half a dozen scientists, or a dozen scientists, or 100 scientists, or 1,000 scientists, all wanting 10 gig connections, you can't do it with point-to-point VLANs because there's no management of it. It's all very manual management. So the Octubre project that we did really focused on how do we get through the issues of making the endpoints understand this kind of bandwidth, hoping that there would be a way for the center of the network to understand it too. And that's, of course, what's happening with the 100 gig networks, is that it allows the switches to do what switches do well, which is statistically multiplex all of this information and get it to the right place with the minimum amount of engineer effort. So that's where we're going. So when we talk about 10 gig, we're talking about enabling multiple gigabits per application, but many applications. And that's really a key thing. So on the UCSD campus, we have been working for, again, many years since Larry and I showed up in the early 2000s, so this is more than 10 years ago, to motivate the campus and the various laboratories on campus to connect with fiber. And as the needs arose and the prices came down, to reach out to them and connect to the supercomputer center to create the systems and networks needed. Now, you had to grow these things based on need. So the ones that we chose because of the scientists who are very involved, of course, of the particle physics folks that are and involved with CERN, and the Ocean Observatory people. We have very advanced microscopy and next generation sequencers on campus. We've got the protein data bank and mass spec data repositories. And then we do all these elaborate remote collaborations. And Lauren will talk a little bit about those today with the digital cinema area. And I know there's been interest in this in Mexico with digital cinema as well. So we'll talk about that in a bit. I'll tease you with a few images, and then Lauren will give you a much more elaborate talk about it this afternoon. So in terms of a picture, this was called the PRISM system, at least before everybody knew the PRISM system is something else that our government does in the United States. But this is a different PRISM. And what it does is it hooks up these places. So the Cal-IT2, which, by the way, has been renamed Qualcomm Institute, at least the part at UCSD did, and that's not because we're part of Qualcomm Company, but because the Qualcomm Foundation, which is an independent operation, has funded us so well over the years, we wanted to recognize that. So you'll hear Qualcomm Institute or Cal-IT2 being used interchangeably, not to be confused. After all, it is about the people, you know. And the building is called Atkinson Hall, so that's yet another. And it's parking lot 503, which is the most important thing for anybody who comes. It's the only thing you can find on Google, by the way. It gets you right to our building. If you say P503 San Diego, it gets you our building codes. That's the most frequent request. People want to know, where do they park? Okay, so we go from Cal-IT2 and San Diego Supercomputer Center, then out to Scenic, as you can see. We go to Scripps down the hill to the regional climate and ocean observing people. And you can see there's multiple 10 gigs. So these are 10 gig links. Some of them are bonded. We have the proteomics group. We've got the physics folks. We've got the microscopy and the protein data bank. So these people are all hooked up, and they're hooked up on these on multiple 10 gig links. These will be upgraded to 40 gigabit links once the medium range 40 gig hardware becomes affordable. We're currently using short range because it's cheap and we can make things work. So we've got this great data now, and it used to be big data, now it's great data. And my goal in life is to turn it into photons. Now, there's two types of photons. There's the ones that buzz along in fibers, and then there's the ones that show up on screens. So in order to create a impedance matcher for all this, because we still need computers in the way, we can't do anything with optics except kind of repeat it, right? So the idea is to build systems that aren't bottlenecks. And so we've designed a system called Fiona. Fiona stands for Flash I/O Network Attachment. It's a PC, but it's quite a PC. It's a PC that's made with a huge amount of flash memory, just like the pieces in Flash Gordon supercomputer. And it sits in our switch colo area because we can talk to it with 40G or with a 5-foot copper cable. And then we also have a Fiona Grande that is a graphics version. And it's used to optimize the networks to graphics processing unit GPU transfers. We synchronize these GPUs to get our 16 to 64 megapixel movies running at real time. And that's a 100G problem right in itself. It's actually worse than that. And we have a lot of 16 to 64 megapixel screens. Just, by reference, that's 1 megapixel, right? So 16 to 64 times that. The bottlenecks shift around. One day it's PCs and in the internal part of the PC, and then you do something like that and you find out it's another part. So Phil Papadopoulos and I have been leading the effort for many years to figure out where the bottlenecks are and to stomp on them and to fix them. So this is what it looks like. So Fiona's, in this particular case, is a rack-mounted PC. It looks like a tower PC there, but it's a rack-mounted PC, and it has a 40 gig connection to their Prism core switch, which is another one of these Arista switches. And then it goes out to the Aristas in the supercomputer center, which then cross-connect to these cloud storage, Data Oasis, and Gordon machines. They also go to our screens, and as you can see, Larry's standing in front of some of his future patient analysis work. And then, but look down there, there's this thing that says, wow, 700. That's 700 gigabits out to the campus labs. So this is a campus infrastructure. The nice part about campus infrastructure is that it's only money. They're really, the politics are small, right? On your campus, you don't have to deal with telecommunications companies and other things that get in the way. Now, I made a slight change here. This is the Fiona Grande. So Fiona Grande has a 6 gigabit per second, 6 gigabyte, throughput. So that's kind of like 50 gigabits a second. And it has 32 gigabytes of, let me go back up. So it's got 4 terabytes of cache memory. So that's the flash disk, 48 terabytes of rotating disk, and a lot of NVIDIA GPUs, which we use for computation. And so, and it is connected to our screens via these GPUs, but then also by 8 times 10 gig bonded links. And the reason why we're not using 2 times 40 is because the cables for that cost too much at the moment. And it's easier just to use 10 gig links and bond them. So this is all built, this is all plugged in and becoming the focus of what we're doing to get higher bandwidth, again, to match these big screens and into the data. Zooming out a little bit, this is the campus, what the campus is look like now. The green up there is new equipment that it says proposed, but we did get the funding. The campus got the funding, so all of this is going to happen. and at least to my knowledge, and are starting in 2014. So it will create all of these extra connections between the San Diego Supercomputer Center and our PRISM system to allow us to push forward. And part of what we're trying to do also is we have a very exquisite group of optics people at UCSD who work under a big grant through the University of Arizona called CIAN, C-I-A-N, and they want to make everything optics, everything optics. And our job, Phil Papadopoulos and I have taken on the job of keeping, part of the problem is when you build equipment, if you take too long, then the commodity stuff just washes over you, right? It just rolls right by you, and you spend 5 years trying to get things up to a certain level, and then you realize you can go buy it at Amazon, you know. So the goal here is to keep the bar high and keep raising it from the electronics point of view. So when the optics people make statements about how they're doing things faster and they need more money to do things faster and more people, that they're shooting high enough, right? So that's part of what Phil and I are doing with the CIAN project. Now, this, of course, ties into the great national and then international networks. We're seeing 100 gig links being built up the West Coast and lit up, and to Seattle, to San Diego, and then across to Chicago and New York. The Department of Energy, of course, has had the 100 gig links for some point now. And then these are being taken to Europe and other places that we're not supposed to talk about yet. Right? Shh, but it's coming. Now, I'm going to switch over now and talk about, how am I doing on time? Are you following me here? Okay, good. And then I'll talk about lots of things. So we've been building these 4K screen modules. 4K is 4 times HD. We've been involved with Lauren and his colleagues building 4K systems for a very, very long time, have had them installed. But you couldn't buy panels until recently that were 4K. So we've been building these things out of pieces. The nice part about this is it folds up and rolls through doors, and you can plug it in anywhere and stick it on a truck and move it. So we do that. And these we can now build and have built in stereo as well. So stereo being 3D. So the 2D or 3D. And we ship them around the world, set them up at shows like this. And this is one booth we made that was entirely out of screens. I think it was the first and last booth ever to be made like this. So you can make these in 2D or 3D. You can have tracking, which means that it follows where you are, so it presents the correct perspective projection in 3D. You can use gesture recognition. You can wave your hands. You can use audio, both voice recognition and audio synthesis for scientific data presentation in the audio domain. And you can make them as wide as you want. We've also designed these things so you can stack them. And so now you can make them 2 systems tall. And this is how we built our system. We have a big space we call the theater, or the multi-purpose room, and part of the agreement in using that space or installing things in that space is it has to be able to come out. We have to be able to remove it. So all of this is on wheels, and we can take it out. Here's an example of the way we normally have it set up. So this is 32 screens. So this is a 64 megapixel screen. And with the computers plugged into it, we can do things like dynamically show billions of points. These are LiDAR points of a building in Florence, the ceiling and walls of a building in Florence, Italy. We showing billions of points allows you to create convincing images out of data that is not polygonal in nature. And that's a big change where we started out showing points when I was first doing computer graphics 40 years ago. And then people got classy and started drawing lines. And then they started drawing polygons and filled in polygons and then shaded polygons and, polygons with nice edges and then transparent polygons. And everything you see that Pixar does is all at some point polygons. But science really isn't about polygons. You actually want the data points. And if you have enough data points, you can show the data points directly. And so this kind of technology gives you a arguably better scientific representation of what you're doing. But you need to be able to show billions of them, because the whole thing with having polygons is you put up the vertices of the polygons, and that was a very compact way of sending data. Is a very compact way of having hardware in the graphics processing units spit out all the in-between points. So we only give just like a vector, you just give the endpoints, it draws everything in between. Polygon, you give the vertices, and it draws everything in between, and so on. But if you can put billions of points out, in my humble opinion, it is closer to the science. Now, Larry Smarr, our director, has Crohn's disease, where we're looking at everything that we can find about Larry. And since he's his own person, we don't run into the same kind of problems with patient confidentiality, because he said, it's me. I'm giving it to everybody. I have health insurance for the rest of my life. You can't take it away from me. And, you can't tell me they're discovering something they're not going to cover. So he is donating this to science, donating his data to science. It's kind of like donating your body to science, but not having to die first. I think it's a really good idea. So this is, he's showing a 3D printed version of the part of his intestine that's giving him all the problem there. And if you can see it, it's a little hook there. That's something he has that many people don't have, and it's a real problem. And it's something that the doctors don't see with the colonoscopies, because they don't see the outsides, they only see the insides, right? Now, this is using the resolution of these screens that we have to put up a huge amount of data, and the idea here is to be able to have all this data and be able to walk up to it. Instead of mouse around it or try to find what's going on, you put these things up in a way in which you can start to see the trends, start to see the ways that these protobacteria and archaeobacteria and other things comparing with healthy people and Larry and other people with Crohn's disease and other people with IBD, which is inflammatory bowel disease, for those of you who aren't up into the tech. So anyway, we are doing a lot of this, and it is about half of what my group is doing now is really working on trying to understand how we get this huge amount of quality data and turn it into things that we can see, bring medical professionals in. The large hospitals, research groups are really interested in this, because this can perhaps help them, the ones that actually care about patients before they get really sick, which are the ones that are HMOs, right? You can help diagnose people as they know beforehand, before they get really sick and need huge amounts of intervention in hospitals. Now, on to other things. Coming through our eyes is large quantities of great data, and that's got to do with digital cinema. I'm going to let Lauren talk about that later, and I'm just going to show you a few images. This is using our big wall to do editing, and these are students editing. And the theme of this workshop has to do a lot with collaboration and how do you work. This is all collaborating with folks and students in Tokyo at Keio University, with whom we've had a very, very long relationship. And this had to do with people discussing life and times and things that came after the tsunami a couple of years ago. We've worked with companies like Skywalker Sound and Disney and so on, and Lauren will go into that, to create these collaborative post-production facilities. Almost done. And again, Lauren will talk more about the Disney collaborations. They're tough customers. You know, anytime you're actually dealing with people who are selling tickets, you know, they're tough customers. And we've done a lot of collaboration experiments between our V-Room and EVL's new Cave 2 system, which I encourage you, if you're in Chicago, to go see. It's extraordinary. And then, of course, to here. You've had an Octuportal here, using Sage for many years, and this was from about 6 months ago. We connected up and had a joint session. So this kind of technology is now available. You know, people can use it. It's kind of our job to encourage our colleagues to use it and to show them the benefits. Now I'm going to take you into 3D for just a couple minutes, and then I'll stop for questions or just go on. We built systems that are extraordinarily expensive over the years, and also modest ones that are portable. So the Tour Cave is so called because it tours around and was developed originally for tourism reasons. And we build these out of consumer panels. Now, the cool part about this is because they're consumer 3D panels, they don't actually cost any more than regular windows. I know this because my wife is remodeling our house, and I know what the windows she wants to put in the house cost. And we could just put TVs there and have virtual reality systems instead, but I'm not winning that battle. But the cost is actually getting down now to a nice car, not a 3-year-old car, but a nice new, say, BMW or something. Right? So this is great because it's consumer tech, consumer PCs, consumer gaming machines, and this is one that's pretty elaborate. You could build this to go all the way around you. The technology supports that perfectly well. And we just finished this one last week. This is called the Wave. And it's pretty big. It's 35 panels, and it surrounds you. It too could be built fully around you if you wanted to. And this is a 70 megapixel system. Now, getting 70 megapixels to do something in real time is again involves pushing all of the technology, all of the networks and the storage and the PCs and the displays and then the controls of it too. So this is what it looks like turned on. This was an exhibit we did and it's a little fuzzy because it's in 3D, you're seeing double. This was done to show paths that the Exodus event may have taken, by trying to sift through real data, archaeological data, and of course the biblical memories in the Hebrew Bible. So I think I'm going to end right here. A lot of work we do from the collaboration side of things is through Pragma, and Pragma is in many places in the Pacific Rim. Of course, we happen to be on the Pacific Rim right here, and Sisese might very well want to get more involved with Pragma because they really do push on building and sustaining the great collaborations. I mean, they really are focused on what your goals are here in this workshop, and they can advance and improve the cyber infrastructure through applications. I mean, I firmly believe that tech is great, but the applications are what people want. applications. You wouldn't buy a PC if it didn't have applications, you know. It wouldn't. We used to. They're talking about the Commodore 64, you know, we bought those, they didn't have any applications, that was fine, you know, but to make the lights blink was great. But now we're more serious, we want them to do things for us. So our research over the many years has been funded by very generous support from NSF, certainly been a large part of my life. KLIT2 and both the director's office that Larry is head of and the UCSD division that Ramesh Rao is head of. We've had many years of very good support from KAUST University and another group in Saudi Arabia that's very much like the National Science Foundation. Argonne National Laboratory, University of Illinois, Chicago, Northwestern for Starlight, that's made all our connections possible. Pacific Wave and Scenic, and many companies. So with that, I'd like to stop, thanking them and thanking you. Yes, go ahead, Leo. Oh, there you go. Lauren. So the Wave is a virtual reality display. It's a 3D display. And in the many, many years, now over 20 years, we've been building these things. To me, the most important part of feeling immersed in your data in 3D is to be able to look down and have it still be there. If you're only looking at something that's in front of you, it always feels like you're looking out a window. And that can be good, you know, it's stereo, it looks like you're looking out a window, that's fine. But the thing to me that really gets you off your feet, you know, that really makes you feel like you're flying or makes you feel like you're inside of whatever it is you're investigating is to be able to look down and, if you can, also look up. Now, you can look down really well. We're really good at looking at our feet, and it's really hard to look up. So you really need to do the ceiling, because you hurt your neck really quickly if you do that for very long. But looking down is a key part of it. It's tricky to do with panels. It was easier to do with projectors. It's just much more expensive and much lower res. So now we have the resolution, which is effectively our human visual acuity, and as good as we can see, and everywhere we can see. Things still aren't ideal. We've got funding to do the ideal system next, so we're working on that. But the Wave was a way to be able to still look down and to be able to look up and look left and right for quite a distance to make you feel immersed. Yes? Sure. So the question is, will the panels come down in price? Well, 3D panels at the consumer level are certainly cheaper by far now than the regular TV panels were a few years ago. So any school that's got TVs, you know, can have 3D panels when they go through the next technology refresh cycle, you know, when somebody decides that they're going to put some more money into it. And they do last quite a while. I mean, for those of you who have home TVs, you know that they do last, you know, a decade. So that's good tech. The chief problem with, so that gets you to the 2D, and now we're getting the 4K screens that are coming out, and they're dropping in price. There's some available under $1,000. The nice part about those is you can walk up to them, and it's just like your Kindle or something. You can have it really close and not get fuzzy. So that tech is coming along very quickly in the way to, all driven by the movie business. The only problem we see with 3D is that 3D has this sort of lead balloon phenomenon every couple of decades in which people get excited about it, do a lot of stuff. And the problem with 3D is that there's essentially nothing in television or cinematic history that focuses on 3D. I mean, people like James Cameron do exquisite work. It's great for documentaries of, places. But, romance actually doesn't look any better in 3D than 2D, and it's so much harder to shoot that it's a tiny fraction. Now, fortunately, doing computer graphics, animations is trivial to do 3D. But doing 3D in the real world is extremely difficult. It changes everything you know about lenses and everything else. And so it may just fail. Right now 3D is effectively free on the television sets. At some point, somebody may say, well, we're going to save, some money and not make it free anymore. And then we're out of luck. So we won't have 3D. It'll go away. And I'm actually very worried about that. I'm running on scarfing up 3D sets before they go away. But if you don't have to do 3D, then it's getting easier and easier. You've probably noticed that the signage displays are just everywhere, including in back of people on every TV set that you see on television. And so that's all going to become ubiquitous and cheaper, just like computers that drive them. Yes?
Cross-border collaboration.
Well, the easiest, you've got two of the problems, the hardest problems already solved. One is the networking, and the other is time zones. The most aggressive people that we work with are 8 or 10 time zones out from us, which no matter how much you try makes life difficult. It's really hard. So we don't have that problem between the United States and Mexico and Canada and all of South America, really. Central and South America, we're close enough. We're only a few time zones off, and in this case, we're very close. So we've got the two worst problems. The next problem is that, if you want to get this stuff done, you got to fund it. It's not going to come out of nowhere. We're all very funding driven, and it at least has to be something that our program officers want. If it's something that they say is required to show evidence of cross-border, like in the United States, in order to get big grants, we have to show pretty much that we work with minority-serving institutions, right? And there's money for that. And to work with states that are called EPSCoR states to get less money. And so we do that, and that helps us get funding, and sometimes it's actually part of the rules. So you had to create rule systems that encourage people because, especially academics, are not going to do anything besides what they want to do unless there's a reason for it. Once you start doing it, and it becomes easy, you get through, it's like learning a new word processor or something. Nobody wants to do this, but once you do it and you realize that it can empower things, that really helps. Now, I've been working in the international arena for decades. And the best part about it is that we don't go after the same money. So if this university were in California, we would be competing with you here. We would be going after the same money from the same people, and we would be very aggressive about it. And the fact that we don't go after the same budget, so we don't go after the same budgets as the Dutch or the Japanese or the European Union people in general, that we each get our own budgets, we get to multiply our activities. I don't think that the scientists realize that, and the researchers, because it's not organized, and that's something that you can do. You're as motivated in creating the highways. You can actually put that forth. You get people to use the technology to collaborate. And the other thing is to not be distressed that it's not happening as fast as you know it can happen. All of this technology takes 25 years to come from the time that people like you, Julio, say, this is a great idea, and write grant proposals, to the point where people would, give up major parts of their life to do without, So if you were, for instance, now to take the internet away from people, they'd get very upset, right? And about 20 years ago, and Larry and I and a bunch of other people were pushing applications on the internet, we get presentations of companies, and these are big Chicago companies who basically said, well, I don't know, this is never going to work. Nobody's ever going to want to use this for commerce. And they were serious about it. They really didn't see how it was going to happen and how it could change, or, how people would type all this stuff into computers, when they had typists with paper, why would you do that? So it takes 25 years. It took 25 years for PCs to make it into classrooms. And, so you don't get discouraged is all I can say. Just keep plugging and do good things and you'll be fine. It's been a pleasure. Thank you.
Thanks. So good morning, everyone, and welcome to the beginning of the 15-minute talk section of the day. So this is going to move very quickly. I'm Nancy Wilkins-Deere from the San Diego Supercomputer Center. I've been involved organizing the Science Gateway sessions, and we have, out of 8 speakers on gateways this morning, 4 of them are remote from 3 different locations. So I will be greatly relieved if this all works by noon today. Jesus is going to be joined by 2 remote panelists, probably not simultaneously, but on the screen here for this first gateway session. So I'm going to go briefly. I think the other speakers will as well. Hopefully you can catch us at breaks and dinner and things for further questions, because I think it is going to move pretty rapidly. Okay, so I'm here to talk about an activity called the Science Gateway Institute that I'm leading. And I've been involved with science gateways, also known as web portals, since the early 2000s. And the way I've been involved is to look at how we could make supercomputers more generally accessible. So instead of leading principal investigators from very prestigious universities and their grad students, now you could have an impact with these large systems to a much wider community because you have these web interfaces in front of them. And so I'll talk a little bit about that. So part of this, supercomputers in the U.S. are often, carefully walled off sorts of things where individuals have usernames and addresses and phone numbers, and you know very well who all your users are. So one of the key things about making this gateway program work was this idea of community accounts. So community or service accounts. So now to the supercomputer, all the people coming in through this web interface look like one individual user. So we now know nothing about the people who are logging, well, I won't say nothing, but we know a lot less about the people logging into these web pages than we did about the hands-on supercomputer users previously. And this took kind of quite some doing, convincing the National Science Foundation that this was a responsible use of the resources, but it's really greatly opened up what we're able to accomplish. And it's increased scalability by quite a lot. So now there's not a lot of user support that we at centers do. Now a lot of this is done by the gateway staff. Lots of publications, lots of impact, not nearly as much personal hand-holding, which is tremendous. What's been interesting about working in this gateway program is that because these things are funded independently and they're not funded by the supercomputing organizations, you see a lot of different gateways from a lot of different domains coming in. So all of these projects have their own funding models. The only thing they have in common is that they're using Exceed supercomputers on the back end. So as a result of this work over the years, since the early 2000s, we would see a lot of these projects kind of come and go, and some that were quite capable, large user communities, still lose funding because they went into this as a 3-year research grant, and now the 3 years are up. And so now what are they going to do, even though they've assembled this large user base? So that led us to start think about some other things that led to the Institute, which I'll talk about here. Couple of quick examples of what some of these gateways are like. So Cypress responsible for a large number, actually, of supercomputer users. So 25% of all the users on U.S. academic supercomputers, NSF funded, come through this one single gateway. Don't use 25% of the CPU time, but it represents an awful lot of users. And what you'll see is that you've got leading researchers from your R1 institutions like Stanford, Harvard, and Yale, but you've also got you're now providing access to people regardless of their institutional affiliation. So you might have, Tom mentioned the EPSCoR states or minority serving institutions. You're now giving this power, democratizing access, we like to say, to people across the board, including, we learned last summer, we had a 15-year-old, you'll see him in the lower left here, this is from when the NSF website was up and working, he won his state science fair by using this science gateway. No help at all, didn't even know he was using a supercomputer, but had a great advisor in high school. And so you're able to put these great tools in the hands of students, which I think is really powerful. GIS is another nice example because we're seeing more and more complex data sets, great data, as Tom said this morning, where you've got layered information that's all important to solving a particular problem. And so GIS is a real up-and-coming area that we see for gateways. A lot of the tools are still desktop-based, so there's a lot of work to be done to kind of elevate that problem-solving environment. And finally, we see a lot of instrument connections. So this one's kind of unique. This is an ultracentrifuge down in San Antonio, Texas. And researchers access this remotely. So they might send samples to this ultracentrifuge to be spun and learn information about its molecular makeup, or they might have an ultracentrifuge at their own site and they're just using analysis software remotely through the gateway. But the nice thing here is that they have their own very large user community. They use supercomputing resources in the US, but also in Germany and Australia, very large worldwide user base. So it's just kind of an example of the uniqueness. So we're the Institute, this is a greatly abbreviated slide set. The Software Institutes, NSF has recently embarked on a funding program for software, and this comes out of the Advanced Cyber Infrastructure Division in the NSF that also funds the supercomputers. They're looking at the importance of software and how many people rely on different software packages, and that's everything from a computational chemistry package to a gateway is software. That's what it is. And so for these things to have the persistence that they need to make scientific advances, they need sustained funding, and you have to think carefully about that because it can be a big black hole if you don't think carefully enough. There was a recent example just yesterday, some of the Nobel Prize awardees were awarded for computational science for the development of the charm code. And for work done, one of the awardees mentioned this was work done over 40 years ago, that he did 40 years ago. So you really have to take the long view when you're looking at funding some of these things, and that can be challenging. So institutes are these long-term hubs of excellence, so something that's going to benefit, rather than a small research code that benefits a small group, something that has a much wider impact. And we thought, looking at gateways over the years and best practices and sustainability and things like that, we thought this was a terrific idea for an institute because it had such broad applicability to many fields. So these are some of the things that we saw in your typical research project where you're building this prototype and you've got some early adopters and people are doing some work with your gateway, and then your research project ends and the scientists who've invested the time are now disillusioned and they're maybe less likely to use technology the next time around. And that can be very detrimental, I think. So we did a little study about this. And I would like to take 6 minutes of my remaining time to show you a short video, because in the context of doing this, we read an awful lot of reports, and we read a lot of reports that had very good recommendations. And that discouraged us a little bit because we didn't want to be just one more great report on the top of the stack. So we thought, how can we make something a little bit more memorable? So I'll hope that you will give me 6 minutes of your time here, and then I'll have 2 remaining slides, and I can show you what we did. Let's see. I'm going to use the audio through my laptop now if the folks in the back are ready. Thanks for indulging me there. Okay, so that presentation really kind of showed in a nutshell what we're trying to do with this institute. So, we have this idea of, a lot of these small research projects don't have all the expertise that they need. So if you have a pool of experts in security and software engineering and project management and marketing and usability, if you have this pool that others can cull from, we think that's really transformative. In addition, if you have a staff, a support staff who can go out and help others build these gateways, so help them get off the ground, help them learn how to get going, and then retreat and move on to another project. We think that's compelling as well. We think there's an awful lot of opportunities for cross-border and really around the world collaborations we have. An agreement with a sister organization in Europe called the International Workshop on Science Gateway Series. So we hold kind of alternate workshops and co-publish in a special journal issue. We're just doing that this fall. So really there's a lot to learn from developers no matter where they're based. So I think as far as the applicability to the network, gateways are an interface over complex resources. So just like you can use them and not know that you're using a supercomputer, you can use them and not know you're using a high-speed network. You're just able to do things that you couldn't do previously. You're able to do them faster. So I see them as an overlay. I think that you'll see that through some of the presentations. And yeah, I don't want to go over time here. Let's see. Let me introduce our next speaker, who hopefully is coming in remotely. So Michael McLennan, I can't see the screen. I don't know if is Purdue on?
Yeah, we're here.
Yes, great. Okay. So I imagine you'll switch the audio so you can hear Michael. Michael's going to talk to us about the Hub Zero project. NanoHub, which we'll hear about a little bit later this morning, is an extremely influential gateway. I think they're up at close to 200,000 users now, a huge impact on nanoscience. And Hub Zero kind of spun off that. So it was looking at using this framework to then allow all sorts of other groups to use the same infrastructure that NanoHub did, but apply it to many different areas. And that's what Michael's going to talk to us about. Thank you.
Terrific. Well, thanks for having me here. And I really wish I could be there to join you in person. Unfortunately, I'm heading out to Atlanta in just a couple of hours, so this is about all we could squeeze in, but at least I could join you kind of virtually over the wire. Are you getting my audio, and can you see the slides okay? I hope so. If you can't, please stop me. So as Nancy said, I'm Michael McLennan. I work at Purdue University. I'm director of the Hub Zero platform and the Hub Zero development effort at Purdue. And I work with Nancy on the Science Gateway Institute. She already kind of motivated everything and told you what science gateways are all about and what we're trying to achieve. I want to tell you about a very specific technology that you can actually use to build gateways. So Hub Zero is an open source toolkit, software platform, that you use to build science gateways. Some people call them collaboratories. We call them hubs. And Hub Zero is kind of the genesis of that, so hence the name. It's kind of hard to explain to people what Hub Zero is and all of the various things that it does. And really the best way for me to explain it to you is to kind of show it to you by kind of flying through some hubs. So I have this video, and I hope you can follow the video with the, hope it keeps up. This is one of the hubs I'm on an earthquake engineering hub at And the here we're exploring a database of earthquake data that was from a Haiti earthquake. Here I'm on a Purdue University research repository where people are sharing data in the project phase. We keep together, uploading files. This is a tool on NanoHub. It's an advanced network simulation tool Gerhard Kornick has worked on. And when you click the button to simulate, it's submitting jobs seamlessly to the cluster environment. You can handle pretty powerful simulation. And when the results come back, they come back with their visualization. You paste them right in, so you don't have to mess around with download files and like visualizers. This is an earthquake engineering tool. You can bring up data from the earthquake, see the sensors that you put on a wall and block the design of the sensors, and do mathematical transformations of sensors. This is a regression testing tool we have that helps you check a scientific model and see if it's misbehaving. In this case, we can see I fixed the bug, I accidentally introduced a glitch into the model, and I can see that it used to be smooth, but now there's a glitch. This is a hub for file fuel. If you wanted to upload something, maybe you have a talk or a technical report, you can just click upload, fill in a title and an abstract, attach your documents, your PowerPoint file, have authors and so forth, and you end up with citable resources. And people have questions and reviews. They say, oh, I love that thing that you just contributed, it's really great. Other people say, I don't understand what you meant by this. You get into threaded discussions and reply back and forth and have arguments online. This is another look at the project phase, and here someone is creating a to-do list item and assigning it to someone as a project, kind of telling them, hey, you need to fix that data. So HubZero really is all of that stuff. It's the toolkit that powers all of the various websites. We have more than 50 hubs now based on HubZero operating all around the world, and all kinds of different scientific disciplines. So HubZero is the toolkit that you use to build those kinds of things for communities, from pharmaceutical to healthcare to nanotechnology to even things like ethics and professional ethics and human animal relationships. So lots of different communities. In fact, here's kind of a grid of all the different communities for all these various hubs. You can see there's a bunch of hubs that are kind of related to engineering, a lot in healthcare, some in the environment, environmental impacts in water, conserving water, impacts on the watershed. Some in education, using STEM education resources, and some that are just related to computing to make it easier to access computing environments. So all kinds of different communities. And if we list those, NanoHub is the biggest hub on that list. As Nancy said, there's more than 200,000 users that routinely use NanoHub just in the course of a year. If you count visitors, a lot of websites count visitors. Those are people that maybe find your site and look at it once. There are 500,000 visitors every year that go to NanoHub. Of those, about 260,000 stick around. Second biggest hub is use. They have 250,000 visitors. They have about 70,000 users that together online for data. But you can see those aren't just cherry-picked cases. There are a lot of hubs that have tens of thousands of users and visitors. And if you add them all up, you get about 1 million visitors total that HubZero supports over the course of every year. So every feature, every change we make is supported. So as I mentioned, Purdue, we have a bunch of hubs. HubZero started at Purdue with NanoHub, and we have a lot of different hubs and use in all of those. We have 27 hub projects that we run at Purdue, but because the software is open source, software is spread to lots of other universities. So you can find hubs at Indiana University, and Notre Dame, Illinois, and Connecticut, SUNY, Buffalo, all kinds of different schools, even different countries around the world, Colombia and India, etc. So there are lots of hubs that people are using the software to create new hubs. And because of that, we've set up a whole other independent nonprofit organization called HubZero. So HubZero is kind of like the Mozilla Foundation. It's the independent owner of the HubZero program. It promotes dissemination and outreach. Every year we sponsor an annual HubHub conference that gets more than 100 people together to talk about the HubZero software and all the changes and improvements. And the HubZero Foundation also coordinates any software contribution. And it's an open source project, so the contributions coming in from the outside world, you can contribute to the HubZero project. You can moderate those contributions and issue them to everybody else. So there are lots of ways to get involved. I don't know if you can actually snap these QR codes, but I tried to put up some resources to let you do that. Number one, you can download the code and have that as a source, so you don't need my permission. Just go to the website. It's at hubzero.org, hubzero.org, and you can push the download button and download the source and have at it. It's actually about 47 Linux packages. We have Debian packages set up. We also have virtual machines set up. So you can download a VMware virtual machine, just start it right up the VMware player, all configured, ready to go. So it's kind of a hub in a box that you can start installing. But if you want to install it on a real machine, use Debian packages, and there are about 47 packages in total for the Hub Zero, all of the Hub Zero software. And that includes not only the web functionality, but all the middleware and all the access to high-performance computing and all of that. Now, if you start building hubs and you really like it, and you want to do more, you can join the Hub Zero Foundation. You can become a principal in the Hub Zero Foundation and participate, and that'll give you up-to-the-minute access to source code improvements, and you can participate in all the monthly tech meetings and help make decisions about Hub Zero in the future going forward. We also have consulting and hosting solutions that we offer through Purdue, and I think there are going to be a few other companies that will be offering that sometime soon. I've talked to a few of the startups who will be able to place the Hub Zero software for you or do consulting at least for you on Hub Zero. And again, if you go to the hubzero.org website, you can find information about the hosted solution. Some people want a hub, they just don't want to mess with it. And so that's when we come in for the hosted solution to help you go out. I had a slide in here about NanoHub, and I was going to talk a little bit about NanoHub. Looks like my PowerPoint skipped over it, but I know Gerhard Klick is going to be telling you all about NanoHub later on today. So I think that's terrific. So I think I'll end it here, and here's our URL, hubzero.org/pressroom. Has a lot of great information, and I'll turn it back over to Nancy. Have a great conference.
Once you got going, though, it's a very good presentation. Thank you. I think we're going to move right along with our 15-minute schedule. We'll look forward to hearing Gerhard after our morning break. So thank you very much. Safe travels to Atlanta.
Thanks.
Our next speaker, who I hope is also coming in, is Diego Scardacci, who's coming in from the University of Catania in Sicily. So he and Roberto Barbera have done some leading work in science gateways for some years and hosted an event in Mexico City in June of 2012. So I do have Diego's slides. I hope that his audio is here. Do we have our next speaker patched in? Unfortunately, our last speaker is here in the room. So
Can you hear me?
Yes, we can. Can we have the I might have to advance them. Can we patch in the video from Italy? One moment, please, Diego. The overhead.
Try to close the call and record to...
Our folks in the Sesezi booth, can we show the slides? They were up on the screen here just before we were showing Michael. You can be all done, Michael. I can display them from my laptop. Why don't I do that? Yes? Okay. Okay, I'm seeing the Italian slides now.
Can I stop?
Yeah, why don't you go ahead and, go ahead and start, Diego. We can see your slides and we can hear you. If we can turn up the volume on Diego and then off of me, that's good.
I'm Diego Scardacci. I work at Interfine Catania in Italy, and in this presentation I introduce a standard-based science kit framework using the Access AC with the cloud resources distributed worldwide. Next slide, please. This is
Just one moment, the audio is not coming in terribly clearly. Is there anything we can do about that? Needs to what? Oh, okay, I think we're still getting the sound from Purdue.
Okay.
One moment, Diego.
Okay, slide 2. This is the summary of my presentation. First of all, I give some introductory concept and driving consideration. Then I will describe you our vision and our use case. And I'll show you some of the current results and highlight the activities in Latin America. Finally, I do some conclusions. Next slide, please. Evolution of speed computing. Thanks to the decrease of the cost of the hardware network and the increase of the CPU power and bandwidth, the way the compute is changed, and we moved from the mainframe to the classic computing, the grid computing, until reach now the cloud computing. Next slide. Thanks to several projects, mainly funded by the European Commission, a global research network has been created. And, next slide please, on top of this global research network, several grids has been built. And each grid, next slide, developed its proprietary middleware. Each middleware, the middleware developed are not interoperable with the one with the other. Then this is a big problem we have to manage now. Interoperability and easiness of access are currently some many uses in the usage of the infrastructure. A similar problem we have in the cloud world. Indeed, we have public cloud stack, private cloud stack, and commercial cloud stack. And all these cloud stack are not interoperable the one with the other. Next slide, please. The China-based project. The China-based project started on the 1st December 2012. The duration is 30 months, and the target region are Africa, Arab region, Latin America, China, India, and Far East Asia. I listed in the slide the main objectives of the China-based project, and in this presentation, I will focus on the first two objectives. Extend and consolidate the international cooperation of Europe with other regions of the world in the domain of the infrastructure, and promote, coordinate, and support the effort of critical mass of non-European infrastructure to collaborate with Europe by addressing interoperability, integration of grid and other DCIs, such as potential programming cloud federation and APC centers. Next slide. Interoperability and interoperation. Some definition. According to the information technology vocabulary, interoperability is the capability to communicate, execute program, or transfer data among various functional units in a manner that requires the user to have little or no knowledge of the unique characteristics of those units. In engineering, interoperation is the step of adopt components and methods to make two or more systems work together as a combined system. Next slide. To reach in interoperability and interoperation, the adoption of the standard is a key factor. Our vision. Next slide. A scientist can seamlessly run application on APC machines, grid and clouds based on different middleware. This is our first use case to demonstrate the interoperability. The cloud tenant of a real organization can seamlessly and easily manage cloud resources fetched by provider or infrastructure based on different cloud middleware stack. This is our second use case to demonstrate the interoperation. Next slide. The Chinese demo contributors. In slide, I show all the contributors of the Chinese demo. We have contributors coming from Asia, from Europe, from Africa, from North America, the future grid, and from Latin America, Gisela. Next slide. This is our first use case. In this case, a scientist can sign in online science gateway using his federated credential, select an application from a menu, and seamlessly execute it on a PC machine with the cloud. The action of execution on the three different platforms can be adjusted to simulate the need to boost their success in case of temporary peaks of activities. The slide. The reference infrastructure uses the EGI federated cloud. Indeed, this infrastructure fits very well with our first use case and our second use case. The slide in Science Gateway framework. In this slide, I depicted the architecture of our framework, where we have users belonging to identity federation, that could be administrator, scientist, or cloud tenant. This user, through our Science Gateway, can exploit some embedded services. These embedded services would be all scientific application. And in this case, this scientific application will be executed on a distributed computing infrastructure through the grid cloud engine based on the OGF standard. Or the user can exploit the cloud services to manage cloud infrastructure, to create, destroy virtual machine, and so on. Next slide. This slide shows the identity federation currently supported by the Science Gateway. I highlighted the identity federation coming from the Latin American world, Café from Brazil and Coffee from Chile. And also, I like to highlight the Educate Interfederation. Next slide. In the context of the China-based project, we worked in collaboration with UNAM and QD to develop the first identity provider in Mexico. And now this identity provider has been successfully deployed and is supported in the Canadian Science Gateway framework. Next slide. This slide, the Canadian Cloud Engine, shows the architecture of the Grid Cloud Engine. On the top of the slide, we have the Science Gateway, where we put the embedded services. This Science Gateway are connected with the Grid Cloud Engine through a Science Gateway interface. The Grid Cloud Engine is the big square in the middle of the slide. This Grid Cloud Engine has two interfaces, one towards the Science Gateway, the Science Gateway interface, and one towards the DCIs. This interface, the interface towards the distributed computing infrastructure, is based on the OGF standard, and in particular, is used the JSAC implementation of the OGF standard. Inside the Grid Cloud Engine, we have three main modules: the job engine to submit application towards the DCI, the data engine to move data on the DCI, and the user tracking and monitoring module to store tracking and accounting the data on our user tracking DB. These API allow us, inside the API, we have a set of adapters, one for each DCI supported, that map the OGF standard API with the proprietary API of the middleware of the DCI we are going to use. For example, if you want to submit a job towards a DCI running the Unicode middleware, the layer based on the JSON API translate the standard API in the command needed to submit the application, in the command needed to submit the application on Unicode. Always in the context of the Chinese project, we worked on these adapters and we updated some adapters already available inside the saga, and we created an adapter. In particular, the last adapter we created is an adapter for OCCI Cloud that allow us to submit the job towards several cloud stack supporting the OGF standard OCCI interface. Next slide. Now I'll show you how to run an application on the EGI Federated Cloud for exploiting the China-based Science Gateway. In the slide, you can see the home page of the China-based Science Gateway. If in the demo menu, we can select the cloud application. After that, we have to sign in on the Science Gateway to be identified, and the Science Gateway will automatically forward us towards the form to submit the application on the EGI Federated Cloud testbed. Inside this form, we have several options, and in particular, we can select the cloud testbed where we would like to execute our application. Then we can select the virtual machine we want to start, and the virtual machine where our application will be executed, and we can choose the application we want to execute. Moreover, we can also ask the Science Gateway framework for a notification via mail of the status of the application. When the application will be completed, the gateway will notify us by mail about that. Next slide. Running application on various types of infrastructure. In this slide, I'm showing the jobs we executed during the Chinese demo. How you can see, we have job executed on different grid with different middleware. We have job executed with on top of EMI July resources, job executed on top of EMI Unicode APC sites, job executed in sites, and so on. In the small picture on the bottom of the slide, I put a complete picture of the world where we can see also the job executed in North America, in the Genesis sites, and in Latin America, in the EMI July and our grid sites. Next slide. This is the Science Gateway already available in Latin America. The GSERA Science Gateway. The GSERA Science Gateway has been developed in the during the GSERA project, and we are working with our Latin American partner to evolve it. Next slide. Indeed, as part of the Scala model, the GSERA Science Gateway has been restored and updated at the UNAM in Mexico and named Scala Science Gateway. The Scala Science Gateway is in progress to be replicated at Lara. As part of the Scala commitment, QE, the Mexican MN, is financing a pilot project for new services, access to HC and cloud infrastructure via the Scala Science Gateway, build a SCADA Science Gateway. The SCADA Science Gateway will be operational by the end of 2013. The SCADA Science Gateway will be connected to the identity provider of the basic advanced connectivity service for size and to all other identity providers being established in Latin America in the context of the ELSIRA project. Next slide. Now some summary, some conclusion. Standard-based interoperability should be enabled not only across middleware but also, more importantly, across computing paradigm with HC cloud, local cluster, desktop, in order to exploit the network as much as possible. Presence gateways successfully bridge infrastructure development according to different model architecture and make them interoperable at the user application level thanks to standard adoption like Saga and OCCI. The MyCloud service allows seamless multi-cloud service operation across different OCCI providing middleware stacks on many sites worldwide. Next steps are creation of the shared storage infrastructure to support stateful virtual machine, allow deployed virtual machine to find themselves in the cloud, fostering the deployment of cloud infrastructure in the regional addressed by channel heads to widen the testbed both in size and geographic coverage, promotion of the TGI the cloud model and possible extension of its infrastructure to other regions in order to support global virtual research communities. That's all. Any questions? Hello? Hello? Can you hear me? Hello?
Yeah.
Okay, I'm going to speak about the project of implementation of a science gateway for national service in Mexico and for Latin America services. The idea here was working in the implementation of different kind of services that are needed in the e-science communities. Okay. The first, about some background, I can speak about the experience in Mexico, working in different kind of grid projects in the past. And two of the most important projects were the Laboratorio Nacional de Grids de Supercómputo that CISESE and other universities were part of this project. And the other one is the Laboratorio Nacional de Cómputo de Alto Desempeño that we have now in Mexico City, joining three of the most important universities of Mexico. In the next, we have the experience gained in collaboration between different kind of universities in Mexico that in 2009, we funded one organization, national organization, in the way of get collaboration between the resource and between the communities that were working in different fields of specialty. Here we get to add around 10 universities, and they were working different levels of incorporation and put a different kind of services and applications shared with their peers. Here is some that around the work that we made in Latin America in grid services. And many of these projects were funded by European Commission, and the work was devoted to build one infrastructure in Latin America in the way of get the support of the research community. Here, one of the most important aims of those projects were to share infrastructure, but the most important were to get collaboration between different kinds of groups in Latin America. At the end of this project, the Gisela project was the last one. We maintain the effort of organizing some infrastructure in Latin America, and we speak about this like ESCALAC, that the means is advanced service computing for Latin America and Caribbean. And the idea is to share different kinds of resources for different purposes. The states of collaboration are here different in each region. We have some countries that have get national organizations for high performance computing, and in another countries we only have a strong community working together, and we have in some countries only resource centers, important resource centers that are incorporated in this project now. This activity are supported and with the facility of NRENS and Clara that are one important infrastructure for share all the kind of services that we are incorporating in this project. Okay. The work in Escalac are now trying to solve some different kind of problems. The first of them is to support the services that were in production during the past experience with another grid projects. Here, the principal aims is to get sharing grids, infrastructure, and network services. But we are now working in the incorporation of new services like cloud computing, high-performance computing, and remote instrumentation services. Many of these are based in the technology used and past showed by Diego Scardacci. In many of the work we are working together and implementing many of these services. But one important problem that we try to solve here is to the incorporation of new services, putting in the framework new applications, new communities are going and using more resources, and they are interested in the use of applications that are not now in the framework. Then one of the activities are the incorporation of new applications, and one more is the meta applications that use different kind of applications, all of them working together. And the idea is to move inside the mobile technologies in the way of we can get more efficient access to this infrastructure. Here was the one slide showed by Diego, but I would like to refer here to, because it is the architecture that we decided to maintain, and the idea is to get the implementation of these different kinds of service infrastructures, and this work is in this level of the architecture. And in the other side, we are working in the implementation of different kinds of applications. Here we have an important column referred to the human resources that are supporting all the work that the researchers are that the researchers requires, and here we can support different kinds of research requirements in the level of infrastructure or in the level of applications. The idea is that the front end can support all of these services, considering different kinds of resources that have a different experience in the use of high performance computing resource. One of the resources that are supported is the grid computing resources that now in SCALAC are sustainable. Presentation not permit to show clearly. But here is the front end for the Science Gateway from the Gisela project and now for the SCALAC project. And here we have a database for the different kinds of applications that were ported to the grid environment. And those applications are shared between different groups in Latin America. And they can use different kind of resource for the experiment that they are running. And here we have the different kind of technology used for this implementation. Many of the presentation of Diego were talking about this, but only one word more is that we use different kind of identity federations that are now wielded in Latin America, and they can use these services. And here is the architecture for the implementation of the application inside of this Science Gateway. Okay, this is the transfer of the Science Gateway for Latin America. This is the required components for this implementation, and they are now working like different services, and we are working on the integration of them in the way of get the Science Gateway service working here. One important aspect of all of this is the virtual research community. I think that it is the principal problem in the focus in the project of Science Gateway, because the communities are now trying to use more and more resources, computational, advanced computational resources, and they need one way of getting the access to that resources that can give more efficient work. And here we were working in the implementation of different kinds of applications. Those applications are only ported to the grid environment, but now we are working in the implementation of this application, of those applications inside the Science Gateway. One more comment here is that not all of these applications are now available because the state of the functionality is different for each applications. But now we are working in the implementation of all of this in the way of get one better platforms for the scientific work. In this way, we identified some communities that we started working with them. Here are the first identified communities, and this is applications that we are trying to put together in the way of strong the collaboration between different researchers that are part of these communities. And here there are some examples of applications in the Science Gateway, Gisela Science Gateway. And here we have the life science applications that were ported inside the Science Gateway. And here there are some examples about the parameterization of these applications in the way of get more efficient access and tools for the researchers, and made the use of the resources more accessible and to the different groups. And here there is another applications ported, and in the science, in the health science, we have two different kind of ported applications. One is an application of modulation, and another one is an application for data acquisition in seismic sensor networks. Then this is in general the work that we are doing here and in Mexico and LA, and I think that this can be a base for stretch the collaboration and maybe organize different kinds of project in the way of get more efficient work and get more results. And thanks a lot.
think we're running a little bit past time right now. We have a break scheduled until 10:15. I'd like to ask if we could still start at 15 after. I hate to cut the break short. I know the first speaker has class commitments. We're going to try to work out the audio. If that doesn't get better, it's not worth. I guess it depends how much you went the break time. Yeah. We have 2 remote ones, and I'm trying to get local copies of the slides and trying to sort out the audio rapidly. It is too bad we couldn't hear Diego's talk because there were a lot of references in what Jesus said to that work. Or Jesus. I think a lot of the gateways are islands, and in some ways that's not a bad thing if they're designed to serve a very specific community. I mean, I think having the developers not be islands and being able to communicate is a good thing. One thing we've also seen for the ones that go to supercomputers is in international scenarios, it's very nice to be able to identify where someone comes from and then have them run on resources that they have access to. So in the U.S., there are more restrictions about who can run, and there's a very large European contingent on some of these gateways. Being able to send jobs there where you don't have the same restrictions is something that we're actively working on. So that could. Yes.
Okay, I'm gonna have to restart, so while I'm doing that, bear with me for a second. So I'm gonna ad-lib some of my slides while it restarts. And then I'm gonna go back to, Bob gave me 10 slides to present, and I'm gonna go back to those. I added a few extra slides about the Open Science Data Cloud Partnership for International Research and Education. And that PIRE is a program at the NSF that funds different types of projects to form international collaboration. And it's appropriate here because although CISESE is not one of our members now, it is certainly a possibility in the future. Let me just log in here. My little computer is so used. I'll blame it on the computer. It's really me. I had a very nice time here last night. I'm back. All right, so here we were, and I was reading some of the characteristics to you about the Open Science Data Cloud. It does have 1 petabyte of science data for the research community, another petabyte of biomedical data for the medical researchers. We've been doubling in size each year. We run production services for NASA and NIH researchers. OSDC interoperates with Amazon Web Services, or AWS, but it's still rudimentary. We have hundreds of users, not thousands, like AWS, and a typical job uses thousands of core hours over 10 to hundreds of terabytes. This is So the split is, as you can see, the Science Cloud has data for earth sciences, biological sciences, social, digital humanities, ACL groups, etc. And then the protected data cloud is the biomedical cloud, and it's designed to hold protected health information like genomic data, not Larry's yet, but that's a possibility. Electronic medical records, etc., and it's HIPAA and FISMA compliant. So what you get with the OSDC, you get login with your university credentials via InCommon. You can launch virtual machines, virtual clusters, and have access to large Hadoop clusters and other file systems as well. Access petabytes of open and protected data. You can manage files, collections of files, collections of collections. You can manage users and groups of users, manage accounts, sub-accounts, and efficiently transfer large data using UDT and UDR. Okay. So the OSDC is under the Open Cloud Consortium, and that's a US-based not-for-profit corporation. Companies such as Cisco, Yahoo, and Infoblox are members. Universities are members, including University of Chicago, Northwestern, and others, including Johns Hopkins. Federal agencies are part of the OCC. International university and government partners have joined. It manages cloud computing infrastructure to support scientific research like the Open Science Data Cloud, and also manages cloud computing test beds. So our point of view, and that's the Open Cloud Consortium and the OSDC, we want to develop as little technology and software as possible. So that should cause a question later. Why do we say that? We want others to develop that software and technology. We focus on providing researchers the ability to compute over large and very large data sets. We need open source solutions. Today, it is difficult to interoperate with AWS for our protected data cloud, but we expect this to change someday. We can run lights out over multiple data centers connected with 10 gig and soon 100 gig networks. Okay, challenges. And no, this is not my PI, Bob Grossman, but he likes the picture. Okay, the Open Science Data Cloud, data centers, and networks. We have 3 data centers in Chicago with 100 gigs to Starlight, at FIU, and that's co-located with Ampath in the POP with 10 gigs to Starlight, and at Livermore Valley Open Campus with another 10. We're planning one more data center with a 100 gig connection to Starlight, and we are looking to interoperate the OSDC with international partners over 10 and 100 gig networks. Challenges. We are focusing on the following. How do we authenticate, authorize, and provide access controls to researchers at our international partners to data and to cloud-based services such as storage and compute? We need open source implementations of these services, and we need trust relationships with our peers. We are running a series of interoperability workshops to try to get this right. So if this is something that you're interested in, you can join our mailing list and learn about workshops. We will be at Supercomputing in Denver in November, so if any of you are there, please come by our booth. And I started to ad-lib about the Open Science Data Cloud Pyre. That's our first slide here. So this is an NSF partnership for international research and education. We received a 5-year award that will run through the end of 2014, and it was for $3.5 million. So all that infrastructure I discussed earlier, it's not from this award, it's from other sources. Okay, so the PIRE prepares students to compete in a global environment, and it's a great opportunity. It provides international research and education experience around the world. The grant pays for their travel and lodging and incidentals. We run a workshop every summer, and it was in Edinburgh last year. Not this year, but what year is this? In 2014, we'll be in Amsterdam. So we create teams of students, faculty, and science researchers, and they help develop some of those challenges I listed for the OSDC, and hopefully stay part of the community over many decades, not just years, but that's where they create peer relationships that we hope will sustain them. We have international collaborators, and they're listed here on the slide. The University of Edinburgh, University of Amsterdam. Can't really see this. It's so tiny. Okay, yeah. Good friends at University of São Paulo, at AIST in Japan, and at the Beijing Institute of Genomics in Beijing, China. Okay. So this grant funds U.S. citizens and residents that are mostly grad students, and it's open nationally. It's not just at our 2 universities. So I've had students from all over the country participate already. And as I said, they'll be going, I'll be recruiting for summer of 2014. And they stay for 6 weeks at one of the international partners if they're accepted. And the selection process is rigorous. We have an application online, and we go over each of the projects with international partners and then select up to 15 students. And some can be invited back for 2 years. And we all, as I said, we're creating a community of scholars. We're on Facebook, we're on YouTube. I tweet if you want to follow me. Heidi L. Alvarez. So it's an exciting program, and we hope to apply for another 5 years with any luck. So if that's something of interest to anyone in this audience, please talk to me about joining. Okay, any questions? I guess I'm between you and lunch. So I will thank you for your attention.
First of all, thank you very much for the invitation to this meeting. I enjoy very much not only the conversation with some of you, but the topic which you discuss. This topic is quite new for me, and we just start research in this area. And I will present some results we presented in IEEE Cloud 2013. So this is joint collaboration with the University of Luxembourg, North Dakota State University, and University of Sydney. So, and I'm Andrei Chernik. I'm from the Computer Science Department of CSESA. So first of all, because I knew in your group, so I present first my team and the background which we are working. So this is the picture from the old time which I start working like an engineer. So some cabling under the floor, the old supercomputer. I participate in design of the chips and the whole system of the supercomputer in Russia, in Moscow. It's quite famous. After that, I start doing something in the data flow computing, the different model of parallel computation, and scheduling finally. So now my research topics, it's around the grid computing, cloud computing, high performance real system, different types of the environment, knowledge, and different approaches, like a multi-criteria optimization approach, or applied some different types of meta-heuristics and so on. So I have some, our groups have some collaboration with different countries, with different teams. We have joint publication, exchange the students, and the staying each with other. And so this is quite fruitful. And our team, mostly it's PhD students, master students, was supported by National Science Foundation. Once we had a project University of California, Irvine, and DAAD, UC Maxos, whatever. You can see that different institute. For instance, the LAFMI, it was with France. So this is some pictures of the team. This is some publications we did in last years. Some journals are very recognized in the world, and so we publish there. So now a bit about results of the proposal which we want to have and make a research. Actually, it's just initial point. How to model application. So now you know that scientific workflows, they usually represented as graphs, different structure graph, of course, different types of data inside and different amount of calculation inside. So we try to take a look inside this type of application. So, and I took one of the slide from the Larry presentation because it's exactly what we are thinking about. So this is a DAC, this is a graph of activity which need to be done to make analysis of the information. So you can see that how complicated this graph. And we don't know, or we could calculate what amount of calculation we have to have in each point and how many data which we should transform. So, and the two known approaches exist. If we take into account the data transfer, this is a communication unaware model and ages-based model. So communication unaware model, so each node of the DAC, of the graph, can represent both computing and the communication. So it's inside one node. It's quite known approach. But the main drawback of this, so we have together and we cannot optimize it very much. So we cannot make a good decision about how we allocate this node. Another node is an age-based model. When the vertex represent the computing and the edges represent communication. And of course, each communication has some kind of the weight or the amount of data which we need to transform. So this is a classical approach. It works very fine if you want to map this kind of graph to the communication system. For instance, if you have some fixed topology, so you can map it. So it exists many, many years. But one of the disadvantages we will mention, so this one, if I produce a data, I cannot to put to different nodes because from the formal point of view, there are two ages. So I need to generate and transfer the data 2 times. So, but the problem in many, this is uncertainty. So these 2 types of the approaches does not work very much with uncertainty. And we know that in a real scenario, everything is changing every time. We cannot predict the quality, the quantity of data which we need to transfer. Even we don't know the resources or the amount of work we need to process. So we don't know exact knowledge about we don't have about the system, effective processor speed, number of available processor, actual bandwidth. This is the worst in a cloud computing. In a cloud computing, everything is virtualized. So it means that user cannot understand in what environment his problem will be executed. And of course, that each physical resource can execute several tasks in the same time, so that effective speed is go down, or the bandwidth. So what we propose now, this is a different types. It's the first time in the literature. We're trying to change the idea. We're trying to propose a DAC which separate communication node from the computing node. So, and the ages, the links between this only for the dependencies or order of execution. So in this case, we can make completely separate decision about how we allocate computing node and what resources, and how we allocate communication node and for what resources of communication. And because we don't know anything, we cannot map it in advance, because it's not static system, it's dynamic. So we need to take decision just in the moment when the task is appear. So we could estimate more or less the situation, what exists in that moment. If we separate the calculation and communication nodes, we can get better decision. So suppose that this is just simple from the cloud computing, it's a webmail. Let's say Google. So when we make a checking our mail, we generate some task. It's go to the system, and after that we need to process this application. And after that we just have to find where is a database which you keep your files, mails. Sometimes it's you need to generate the advertisement and whatever, and after to send you in a database, and after to receive data. Of course, you can more or less estimate the structure of the task, the sequence of your jobs, but sometimes you just receive 0 mails, sometimes you receive gigas mails with the attachments, video, or the files, and so on, and you cannot predict it. So you need to work in a situation when you don't know many things. So now we try to make a separate decision about the mapping or allocation or resource provisioning for the communication node and for the calculation node. So we have network and processor, and we make a schedule. So we can see that make span at 7, this simple example. Make span, it's a maximum time for execution all tasks. So if you take another model, communication unaware, when each node represents both communication and calculation, so we make a schedule, and the make span is 9. So another one, another representation, it's a more classical representation, is a duck, weighted duck. So, and we have make spent 8. So if we compare schedule, we can see that our approach in this specific example is giving the better result. But we assume that when you work separately in a communication node as a communication task and a calculation task, we can get better decision, because there is a technique to find better allocation based on a certain criteria. When you choose what resources you want to use, you can use one criteria, you can use multi-criteria. So for instance, now it's very popular to minimize energy consumption. So this we can make a big criteria allocation. So one of the some small disadvantages of this approach, it's easier. In other approaches can do it the same, but it's easier to make a parallelization. If you represent communication as a separate task, when the task is arrived, I can divide it by blocks, whatever, by bytes or what you want. And after that, to allocate to different paths, to allocate different elements of the communication system. And of course, you can do it much easier if you divide in some blocks of communication. So if you parallelize the communication, because in some classical approach, I map to a communication system, but in a real, so you divide in a packet. If even you don't want to do it, it's what has happened inside the network. So it means that if we allow to do it more flexible, or we can do it by ourselves automatically, it will be more efficient. So, any questions? What kind of changes or what approach? It depends. You know that the problem of the schedule, it's a problem of optimization. And the first, you need to ask, what's the criterion optimization? So if you want optimize the time, it's one approach. If you want to optimize, let's say, response time, it's completely different, or waiting time. Throughput, it's different. So you cannot answer that this one, it's a best strategy for everything. So you must to choose what you want to optimize and what you want to have better. If you make a several decision or several criteria, so there must be in conflict. It means that if you try to optimize one, it could be worse than another one, and so on. In this case, there are several approaches to do it. So, and this is like a compromise between the several objectives. But I cannot tell you, so of course we do a different scenario. Of course we do it simulation by statistical analysis. We apply different statistical techniques to understand what is statistically important or not important for the telling that this is a better than another one. And in what kind of class of scenario or kind of application exists. So before the preliminary result, we did by generation of a lot of different ducks and from the several classes, for instance, which I mentioned, the scientific workflow, we took the generator from the Eva Dillman. So we start collaboration with her, and so we use it for the simulation. But of course, it's not reality, but somehow scientists never work in reality. So always imagination. So, some more questions? Okay. Okay, thank you.
Hello, everybody. My name is Mauricio Carrillo, and this is the second talk that was scheduled on the category of life sciences. And I changed a little bit the title and the content of my talk because I thought this would be more appropriate for the audience instead of going into all the details that I had originally planned. So the new title is Computational Biology, Computation-Based Discovery in Molecular Structural Biology. So Nancy mentioned earlier about the novels in 2013, and I didn't want to take this slide out because it talks about three main concepts that I'm gonna go through the rest of my talk. And the first one is that in biology now a lot of experiments are taking place in silico. That's one really cool thing. And this implies that we have to do a lot of modeling and numerical simulations. And the last one is something that some people are already stating, which is that computers were made for biology. And I'm going to talk a little bit more about that later. So I'm a physicist, actually, by the way. I graduated from physics from the UABC, so down the road, across the highway. So it's a really nice opportunity to come back and, talk to you here in CISESE, because I always look up at CISESE being there at the beach, taking physics classes, so it's really nice to be here. So I am really interested in understanding how the machinery of life works. And as I said, being a physicist, I'm pretty much interested in trying to understand what are the relationships between all the interactions that take place inside the cell, trying to understand what are the relationships between the structure of biomolecules and their dynamics, intrinsic dynamics, and their function, actually, at the end. So I'm sure all of you agree with me that understanding life is a big challenge. I would say actually it's a huge challenge. But it also involves having big data, and this needs to big networks. So for those of you who doesn't know, well, I come from a research center called Sinvestab. Sinvestab is a government-funded research center, and the National Genomics Laboratory for Biodiversity, or LANGEBIO, it's one of 8 different units across the country. And our main purpose is to make a difference in the study and sustainable use of national biodiversity, because Mexico is one of the countries in the world with the biggest biodiversity known. So talking about life, so life has many different scales, like from atoms and molecules, going up all the way to the cell, obviously, an organ, organisms, population, communities, ecosystems, all the way up to the biosphere, right? And each one of those scales has an associated computer discipline, to put it like that. And when you think about computational biology, people always think about bioinformatics. But what I'm showing you here in this figure, or the message that I want to send you, is that bioinformatics is only one small portion of what computational biology actually means or encompasses. So we have bioinformatics, which deals with the lowest scale, which is the genes, the genome of the organisms. But like if we go up, we can find other computational approaches to these different life scales. And what I am basically, and you know, like the tools that I use every day, it's what's called the molecular modeling, which involves molecular dynamics or Monte Carlo, all of those numerical algorithms to make simulations of biosystems. But there are other upper scales like metabolic networks, Bayesian models, complex networks, all the way up to phylogenomics, which deals with trying to understand how life evolves, basically. So I'm going to focus today on the level, the scale of molecules and organisms. And Larry already mentioned this, but I'm going to talk a little bit more about, because Langeview has one of the largest sequencing facilities in Latin America. So we do a lot of genome sequencing too, and that means that we generate a lot of data. And there are some limitations, actually. One of them is the one probably the most important right now, which is bandwidth, because we have, or we want to send all of these results to the users. And so transferring this is a big problem now. There's also the computing limitations, but that's not that much of a deal. Also accessing international repositories like the NCBI, it's another thing that it's limiting us now. And as you can see, like the size of the data, the information that it's out there, it's huge. And in order for us to make use of it, it's really hard because we are not, or we don't have the correct connectivity. And this takes me to this concept that I want to mention, because we have a lot of data, we have a lot of information, but that doesn't mean that we know stuff. So we must follow some process in order to use all of that information, all the data that is being generated around the world, to convert it into knowledge that, you know, that we can use to do something useful. And in the case of biology, computational biology is the bridge that helps us to go from information, all the data, into actually generating some useful knowledge. So what is computational biology then? It's a new field, actually. It started, let's say, last century. And some people might say that the computational biology is the result of the 21st century revolution in biology, where many disciplines are combined, and the unifying force is all of these computational sciences and informatics, okay? And I would say that the sooner we realize that biology is a computational science, the sooner we will be able to start approaching these big challenges in biology. And in order to do that, we have to think about creating new paradigms, and that means a lot of collaborations, okay? And we have to take these multidisciplinary approaches. Otherwise, we won't be able to solve these big problems. And specifically in my lab, as I said before, we are interested in understanding the relationships between molecular structure, dynamics, and function, which is by itself a big challenge. We've been using what it's called now the hybrid approaches, in which we integrate in silico, in vitro, and in vivo experiments in order to, in a synergetic way, trying to solve all of these things. And I am showing you here a lot of disciplines that we use every day, and I'm obviously highlighting big networks because each one of these disciplines generates a lot of information in its own, and we have to transfer that from one place to another. So the roadmap which I'm showing here is basically the philosophy that we follow. We use basic research to generate knowledge at the molecular level, and we use that then to rationally create technology and then develop new drugs, because one of our main goals in the near future is to have a big impact in global health. And I'm going to show you one example that you could say it's a success story. And I apologize because this slide is in Spanish, but I think everyone can kind of like understand what's the message here. So we start a few years ago working in this innovative research system in which the objective was to design a new drug which could replace the current treatment in systemic fungi infections, because the drug that is used now, it's very effective, but it's very toxic. So you have to be very careful how people use it. So the idea was to design a derivative that would not have that toxicity. So we implemented this innovative research system, which involves, as the first step, this research cycle with many steps, and each step it's in charge of a different group, which is expert in its field. And the innovative part, I would say, is that introduction of this molecular modeling, because that allows us to understand how the molecular processes of how the drug acted were, and then that gave us some good ideas of what to modify in the molecule in order to take out the toxicity. And that's what we did, and we followed this research cycle. And then we found that after 20 first cycles, we found the one that was useful. That's why we call it the A21. But anyway, we got the patent, and then we are trying to commercialize the product. So this puts us at the frontiers of bioengineering, because as I said, we believe that if we understand what are the molecular principles of this machinery of life, we will learn how to design new biodevices like markers, nanostructures, antivirals, and so on. And also at the frontiers of life sciences, the trend now is trying to integrate the different components of the machinery of life. So we've been successful of making simulations of the whole ribosome, for example, but we also we want to take the next step, which is, okay, so can we model the nucleus of the cell or the mitochondria? But what about the whole cell or an organism or even the world? So there was a previous reference to this movie, but I think it's very clear what I'm talking about when I say simulating the world. So there will be a point where we will have to make the decision of the red or the blue pill. So, okay, so I also want to say that we are limited, and I feel that we are isolated in terms of data, data that we are generating, data that other people around the world are generating. So there is a huge need for big networks, for better bandwidth, and to connect all the people around the world. And well, I want to mention that some of our partners, obviously we have partners in Mexico, but we also have partners outside Mexico. For example, we collaborate with the Argonne National Laboratory. We collaborate also with the Scripps Research Institute here in San Diego, and other universities in Europe, Groningen, for example. And many of these HPC centers, which we have one, but it's not enough, we cannot use because it's very hard to connect and to transfer all of this information. So that's another reason why these big networks are needed. So I also want to thank all the people in my group. And I'm gonna stop here. And Well, if there are any questions, I will leave this movie to show you this concept about the virtual microscope, to show you all the things that can be done using HPC and big networks. So this is just a sample of the stuff that we do. So if there are any questions, I'll be happy to answer them. Yeah? Uh-huh. Well, usually what we do is, like, if we generate a lot of data locally, we just put it in an external hard drive and FedEx it to whatever needs to be analyzed. No, yeah, it's really. Well, we are not connected to these advanced networks, so we use like commercial internet, which actually in my house I have better bandwidth than in the institute, for example. You see, so it's as if we had no connectivity at all. And well, you know, we've been working on that for the past 2 or 3 years, but well, hopefully soon we're gonna improve the connectivity, but I think that we are always going to be behind the rest of the world because, in my opinion, government doesn't understand the importance and the need that science in Mexico needs to, you know, to be at the same level as any other part in the world. So it's a big problem. It's a serious problem. So if we don't do something now, we're gonna be behind, like, you know, in a serious way. Any other questions? Okay, so this is a view of this virtual microscope of the antibiotic that we developed. So this is one of the first stages where we made the molecular modeling of this antibiotic, which is called amphotericin. And it's the current drug used in all advanced systemic fungi infections. And as I said, it's a very effective and potent drug, but it's very dangerous because it's also very toxic for mammals and humans. And so through this analysis, these in silico experiments, we gain knowledge of how it kills the cells, and we were able to design a derivative, a chemical derivative, that it reduced considerably the toxicity. So, as I said, this is a very powerful tool now that we have to, in my case, which I'm interested in having this big impact in global health, could help to do, you know, to produce new drugs, safer drugs. And this is one example of antibiotics, but we're also interested in understanding how viral particles form, so we can rationally design antivirals and in that way try to eradicate viral infections. So we follow the same philosophy that I show you, like through basic research, generate knowledge at the molecular level, and then with that, we can rationally propose different molecules or modifications to the molecules that we know. We do have at Insight a small cluster, medium-sized cluster, which I would say runs like 24/7. It's at full capacity. And last year, for example, we had to buy a few nodes with 256 gigabytes of RAM because we also have to do the assembly. Like if we want to sequence a genome, The sequencing equipment gives you like tons of reads, which are like these small segments that we have to later assembly in silico. And all the algorithms that are used now, as far as I know, needs a lot of RAM. So we also need like special equipment in order to do that. So we are like slowly growing the capacity of our cluster, but as I said, it's not really enough. And many of these in silico experiments, we also use other HPC facilities in Mexico and outside Mexico, but it's hard to use them. Well, like if we will have like 1 gigabyte bandwidth, I think it would be like completely used constantly, like quickly. And that would give us like, like a good start. But as I said, I feel like we are always behind everybody else, so I would say like if we are going to do something, let's do it the right way and not think in the, like to solve the problems that we have now. I mean, that would be nice, but I would say, okay, let's think about like, what are we going to need 10 years from now or 15 years from now and work on that. So it's not, as the way I see it, is not trying to solve the problems of today, but problems of tomorrow. Okay, thank you.
Está muy sensible. Hi, everyone. Now is the turn from Earth Sciences. The next talks will be about the earthquakes and GPS and something like Earth Sciences. Okay, my name is Victor Wong. I am from the Seismology Department of Earth Science Division at CISESE. My talk will be about earthquakes and monitoring and share data with another institution, okay? And how many knows Baja California is in the border of two tectonic plates, Pacific plates and the North American plates. For a long time, we are recording seismic activity, and this could be very dangerous for populated areas like cities, Mexicali, Tijuana, inclusive Ensenada, could be suffer and big earthquakes between 6 and 7, like the earthquake that occurred in 1910. Okay, Grisha? Okay, after the big earthquakes that occurred in the valley of Mexicali and the Cucapa Cucapa and the mountain of Cucapa and the fall of Cucapa, these ruptures went one 7.2 earthquakes. Okay, and these earthquakes show us that we don't have a very good networks, seismic networks, and then many of the many of the population of this local area was affected for the earthquake, mainly in the drains of water drains in the valley. Well, these people and Mexican government and people from USGS and Senapred is a Mexican institution for prediction of earthquakes. It's a mega project to put a new seismic station in real time. That includes 23 accelerometers in cities like Tijuana and Mexicali. Another one is a broadband and accelerometer seismic station in the Mexicali Valley and the Baja California state. That includes Ensenada, from Ensenada to north. Okay, this agreement, the collaboration with Caltech, Senapred, and CICESE is to monitor the earthquake in the region. Okay, for many times, CICESE is collecting seismic earthquake data for 25 years, and we know where the earthquake occurred, but we don't know when. For that reason, we need to continue monitoring the earthquake about 24 hours, 7 days a week, and to observe if this seismic activity changes and the behavior through the time. Okay, so what we have now a big network. Includes about the acceleration can be measured acceleration and broadband seismic station to know where the earthquake occurred. Well, what is next? We need to transmit the data to CICESE. This is challenges to do how? Is by radio, by telephone, by commercial internet, or about satellite internet. Well, we now, in this picture, show us the station, the 6 channel, the recording data. It's 3 acceleration and 3 velocities. Well, this 100 samples per second, 20 bytes of resolution. This is the station, the new station from CICESE, and what is the service we will provide to the peoples and the government and the other interested in the earthquake data from Ensenada, Baja California. Well, this we developed some to see information about SMS and web pages to people, media, and authorities. Now, right now, is working. We are in the lab of RESDO, Red Sismológica Noreste de Mexico. We are working on to make more ahead about the shape maps. That is a distribution of the high intensities in the maps. Okay, that data is shared with another institution like Servicio Sismológico Nacional, the seismic network of Southern California, operated by Caltech, and others like the Senapred. Well, what is the objective and the seismic monitoring? Okay, we know where earthquakes is occurred, the origin time. This is a web propagation about these pictures. We collect with satellites, and then we analyze the data. This data is sent to the information flows, telephone instruments or about the page, and we show us what is the data and look for people, seek for a safe place after the earthquakes, okay? Well, what means sharing data, scientific data? Well, CISESE and USGS will deploy this information sharing system to be better prepared when a seismic may occur. This is the project is to know where the earthquake occurred in the north portion of Baja California. Okay, this implied to transferring very large data volumes that among institutions, the other of hundreds of gigabytes for this middle of the year. We are installing right now 22 stations in real time. And what we need is a very good and big data network links. This will be implemented with the high-risk civil infrastructure for research and development. We are now working on this type of implementation. We know about the sharing data with USA, like Caltech and other institutions, and also represent for Mexico in order to share information between institutions. Okay, well, that's all what I have to talk about this seismic network in Baja California. Thank you. Do you have questions? Well, was so clear? Okay. Okay, this data is transmitted to CISESE by satellite, internet, or to commercial internet by telephone lines. Oh, sure. This is the idea to transmit the data about the more specific big networks with USA. Okay. I don't know, maybe other institutions with Internet too. We are call it Internet too. How we do now? Well, we are sending data to Caltech and the Southern California station close to the border. They are sending this data to us. And the Servicio Sismológico Nacional is sending the data that collect with the instrument that they have in Baja California too. And we share the data between Seismic Network Mexican, the CISESE network, Caltech network, and Servicio Sismológico network. That's the question? Okay. Another question? No? Okay, thank you.
I am Javier Gonzalez. I was born in the border in Mexicali City. Then I don't know exactly how to talk in Spanish or how to talk in English. Because I best talk in Spanish, I will give this talk in Spanish. And after some time, I will say things in English. Quiero agradecer la oportunidad de trabajar con mi hijo, Alejandro González Ortega. Si no fuera por su upgrade en los últimos 10 años, yo estaría todavía en el siglo XIX. Vamos a tratar de dar una idea de lo que hemos hecho en las redes de GPS que empezamos a trabajar en colaboración, como podrán ver ustedes, con diferentes instituciones, principalmente de California, a lo largo de más de 23 años. Hemos estado utilizando el sistema de posicionamiento global satelital por esa cantidad de tiempo. Empezamos cuando todavía el sistema de GPS estaba en su proceso de formación, allá por los años 84, 85, 86, que se empezaron a hacer los primeros estudios para estudiar la separación del Golfo de California, esfuerzos realizados por el Jet Propulsor Laboratorio de la NASA. Desde 1993 y en este caso hasta 2008, nosotros ya como institución que estudia la sismología, la geodesia, la geología del norte de Baja California, empezamos a tomar la responsabilidad de los estudios de geodesia utilizando básicamente las estaciones GPS. Perdón. No sé usar estas cosas. Bueno, aquí, esta es la estación que le mencionaba a alguno de los compañeros que están presentes en esta reunión. Tiene aquí trabajando cerca de 13 años, está a menos de 50 metros de este auditorio. Estaciones como esta, estaciones permanentes y estaciones temporales, nos han permitido tener un panorama de cómo realmente se mueve, como mencionaba Víctor, en nuestra región, incluyendo el sur de California, la placa Pacífico y la placa norteamericana. Simplemente lo que hemos intentado hacer en nuestra región, junto con los colegas de California, que han impulsado suficientemente esto, es utilizar las nuevas teorías sobre tectónica de placas y estas nuevas tecnologías utilizando los sistemas de posicionamiento global satelital para comprobar de una u otra manera los modelos teóricos de tectónica de placas, que por cierto uno de los creadores del primer modelo hace 40 años fue el doctor Bernard Minster. En su tesis de doctorado hizo un modelito que resultó finalmente después en el Relative Motion Number 1, que fue un precursor de los modelos de placas. Nosotros hemos hecho esta contribución, digamos, todavía para mí, pues de las más importantes, porque siendo poseedores, digamos, o por lo menos garantes de la Isla Guadalupe, hemos tenido la oportunidad de hacer observaciones en Isla Guadalupe, que se supone que es, digamos, está viajando, pudiéramos decir, ya con la placa Pacífico, de tal manera que Isla Guadalupe puede ser que, digamos, como un faro que nos dice cómo van viajando, en este caso, la península de Baja California, el Golfo de California y la placa norteamericana con respecto a este punto que consideramos ligado a estos otros puntos en la placa Pacífico. Esta es la instalación, que por cierto, desde hace cerca de 8 años no tenemos comunicación satelital y no hemos podido mantener en operación esta estación, obviamente por falta de fondos. Por esfuerzo no ha sido. Ahora, y aprovechando precisamente este foro, digamos, en el que nos preguntaban que qué pudiéramos hacer para el futuro. Pues yo me preguntaba, bueno, pues yo ya tengo 35 años en esto, 36 años, para el futuro para mí puede ser mañana. Pero digamos, pensando en unos 5 o 10 años para las gentes jóvenes que nos vienen a preceder, pues si con GPS hemos realizado estos trabajos y tenemos idea para, digamos, hacerlos en tiempo real, que podamos medir con estos GPS y otros aditamentos, digamos, el nivel del mar, que podamos medir, digamos, el contenido de vapor de agua y hacer un montón de observaciones que se pueden hacer con tecnologías de GPS, pues me imaginé yo, bueno, pues vamos a participar en este simposio de Big Data, Big Nervos, y pues vamos a decirles a los compañeros que pues vienen ya otros sistemas que, como el GLONASS, es el ruso, que se empieza ya a utilizar masivamente, el sistema COMPAS chino, que está en su experimentación, el sistema Galileo europeo, que pues ha tenido problemas de financiamiento, dado el problema de la Comunidad Económica Europea, pero que pues una vez que ya se resuelva el problema ahorita del bajón monetario en la administración Obama, pues esperemos que todo eso funcione junto con la modernización del sistema GPS. Entonces hay un futuro muy importante para la comunidad de ciencias de la Tierra, el uso de estos sistemas satelitales para obtener precisiones de incluso 1 milímetro en 3D y tan rápido como una fracción de 0.2 de segundo, si así lo quisiéramos hacer. Es decir, este sistema ya combinado nos podría, digamos, ser capaz de dirigir el aterrizaje de un avión a 1 centímetro de precisión. Si eso no es importante, pues ustedes díganme que lo es. Nosotros hemos trabajado por mucho tiempo en colaboración. Como les decía, yo pues nací aquí en la frontera, estoy aquí en el CICESE prácticamente desde que se fundó porque está aquí en mi territorio, en Baja California. Entonces, desde un principio pues he trabajado con personas de la Universidad de California de San Diego, fundamentalmente con los creadores del Southern California Integrated GPS Network, que es el doctor Ken Hudnot, el del Geological Survey y Caltech, y el doctor Yehuda Bo, que está en la Universidad de California de San Diego. También hemos tenido contacto con el Instituto Nacional de Geografía y Estadística. Uno de nuestros compañeros, que siendo estudiante del MIT, ahora nos apoya desde la Universidad de Arizona, en Tucson. Y obviamente de Caltech, aquí tenemos a una representante, Joanne Stock, que desde un principio, desde la época en que se estaba formando la red sísmica de Caltech, desde la época de Carl Johnson, allá por los 75, 76, estamos en colaboración con ellos. Este es un resultado de la aplicación de estas técnicas. Víctor Wall mencionaba la cuestión del temblor del 4 de abril, digamos el temblor MC, le llaman en Estados Unidos, es el mayor Cucapá. Y aquí nos representa las deformaciones producidas por este temblor, es decir, los desplazamientos producidos en el terreno en diferentes puntos donde hemos estado midiendo con estas estaciones sencillas, el GPS, como esto, por ejemplo, aquí cerca en el Chinero, aquí en este punto, que después del sismo pues vamos y observamos esto y podemos observar desplazamientos tan grandes como 1 metro y 30 centímetros, digamos, de la estación La Puerta, que está muy cerca de la fuente del sismo. Es el temblor que rompió alrededor de 120 kilómetros desde este punto hasta aproximadamente el delta del río Colorado. Esta información obviamente pues nos ayuda mucho a la cuestión de la sismología, el estudio geológico, el estudio tectónico de toda la cuestión, no solo la cuestión sismológica del movimiento instantáneo, la cuestión que mencionaba Víctor, de la magnitud, de dar la información, etcétera, sino que nos permite hacer estudios a más detalle, digamos, con estaciones de este tipo, pues ver cómo se va relajando la energía de este temblor, así como lo mencionaba el anterior expositor, de cómo a nivel, digamos, de células, luego se va hacia el ADN y cuestiones de ese tipo. O sea, una vez que se estudia la ruptura, pues ver cómo esta se propaga, digamos, a lugares más lejanos e incluso cómo puede afectar a zonas como, por ejemplo, aquí la falla del Sinore, que pues está precisamente aquí en Los Ángeles, digamos, por acá, que por cierto el doctor Bernard Miste pues paraba aquí su simulación, no era la pregunta que yo hacía, ¿por qué no nos vamos hasta acá? Pero pues eso precisamente es el objeto de esta reunión, hacer más énfasis en la colaboración entre nuestras instituciones y fundamentalmente, pienso yo, no solo la colaboración, sino obtener fondos comunes para aplicar estas cosas. Les mencionaba que somos capaces, o este sistema es capaz de, digamos, ahorita estamos tomando una muestra cada 15 segundos, pero pues se pueden tomar muestras, digamos, de la información que envían los satélites en estas estaciones, pues tan fuerte como 5 Hz, 100 Hz, etcétera. En este caso, o sea, 100 muestras por segundo. En este caso, una de estas estaciones, que no recuerdo, sí está, es esta, que es de la red del sur de California, que antes se llamaba Southern California Integrated GPS Network y ahora es Play Boundary Observatorio. El financiamiento pasó de California a Colorado a través del National Science Foundation, que anda por acá. Y pues independientemente de cuándo sean los recursos, son equipos que necesitan estar por mucho tiempo. Les mencionaba que la estación que tenemos aquí tiene 13 años, pero aún así sin mantenimiento importante y sin financiamiento importante, pues siguen funcionando. Esperemos que este tipo de infraestructura, que está por terminarle su financiamiento, Play Boundary Observatory en Estados Unidos, porque ya empiezan a recortar gente, pues de alguna manera se puedan conseguir fondos para mantener los datos. ¿De qué sirve obtener datos si la infraestructura no es soportada por long term, como dirían los compañeros norteamericanos, ¿no? Y efectivamente se pueden generar más datos en todo el área. Yo preguntaría, ¿para qué sirve más y más capacidad de información, de datos, de computar, si no tenemos los medios de observación para digamos, utilizar esa información nueva en los modelos que utilizan computadoras de 100 gigabytes y cuestiones de ese tipo? Estos instrumentos, mencionaba a alguien por ahí que desde el punto de vista sismológico, lo que mencionaba por ejemplo Víctor Wong, de estaciones de banda ancha, de estaciones acelerométricas, pues esos equipos por sus condiciones de carácter electrónico, dinámico, etcétera, pueden ser saturadas, como la estación que se encuentra por ahí pegada a la estación esta es la estación sismológica de banda ancha y esta es la P496 de GPS, y vemos aquí cómo la estación de banda ancha pues se saturó, de tal manera que esta estación, por ejemplo, no puede servir para estimar la magnitud. En cambio la nuestra, pues sí. Digamos la nuestra, digamos desde el punto de vista del dominio de la geodesia comparado con respecto a la señal sismológica, al fin de cuentas pues ambas son lo mismo, ¿verdad? Estas aplicaciones no solo se dan para la cuestión de sismológica, que es en el departamento en el que yo laboro, sino se dan para múltiples aplicaciones, entre ellas la meteorología. Es decir, una de las, digamos, herramientas ya a través de la NOAA, que se utiliza como información para la cuestión de las tormentas, es el contenido de vapor de agua. A ver, les digo que no sé usar mucho estas cosas. El contenido de vapor de agua, que de una u otra manera, digamos, esta es la presión medida aquí en una de las estaciones del CICESE, creo que es en el sitio este que tiene ahí Higareda, en negro, arriba de oceanología, y esta es la observación de contenido de vapor de agua utilizando la estación esa que les mostraba ahí. Entonces, digamos, aquí se ve un paralelismo extraordinario que nos indica, digamos, con unas 4 horas de anticipación. Aquí tienen la escala de tiempo, aquí creo que son 2.000 minutos con respecto a algo, y estos son 2.500 minutos después de cierto algo, de tal manera que, digamos, aquí claramente se ve que el contenido de vapor de agua va aumentando espectacularmente, sigue aumentando en determinado momento, la presión baja y viene el tormentón que se avecina. Entonces esto, el GPS también, entre otros aspectos, pues tiene esas cuestiones de particularidades para estudiar. Incluso, pues, si sabemos que ese es un gas invernadero, pues podemos hacer cuestiones de estudios de cambio climático también con este tipo de información. Finalmente, digamos, como parte de las ideas que nos propuso el doctor Víctor Bon, jefe del Departamento de Sismología, es, ¿y qué tal si integramos toda esta infraestructura que el CICESE ha logrado obtener, no solo desde ahora, después del temblor, sino desde hace 30, 35 años que empezamos a transmitir en tiempo real? Yo creo que fue una de las redes a nivel mundial que hicimos eso al principio, transmitir en tiempo real la señal de las estaciones, digamos, aquí en Mexicali, a través de San Pedro Mártir a Ensenada, o a través de la red de microondas a Ensenada. De tal manera, aquí está uno de los promotores de aquella, no solo promotores, sino hacedores de Carlos Duarte, de aquel esfuerzo que logramos desde 1979-80. Volví a lo de Víctor Bon. Esto es tratar de integrar todas estas estaciones. Por ejemplo, las rojas son estaciones de una red de Mexicali que ha estado obteniendo directamente con el gobierno del estado uno de nuestros investigadores, que es Luis Mendoza. La red de acelerómetros, digamos, que ha estado operando por mucho tiempo el doctor Luis Munguía. Y lo que es RedNor, que digamos es la red orgullo de ciencias de la Tierra. Bueno, ¿qué tal si dentro de esas 19, 19, 19 y 19, como alguien lo mencionaba por ahí, porque curiosamente son 19 acelerómetros, 19 bandas anchas, 19 GPS, pues tratamos de juntarlos, ¿verdad? Nos acaban de hacer una donación de 50 GPS que provienen de la Universidad de Sorte en California, y a través del USGS, de los proyectos estos realizados a través del temblor precisamente y con el Comando Norte, se han donado 12 GPS que utilizan ya, curiosamente, no sé, tecnología rusa, Javat, y eventos y sistemas, no sé cuánto tiempo tengo todavía, que van a incluir, digamos, como estaciones, ya mencionaba parte de don Víctor Bon, estaciones integradas. Bueno, what is next? Really, we don't need more computing capacity, really. Because when I was in MIT almost 15 years ago, as a visiting professor, I made the processing of the GPS signal using all the computer system of the Earth Sciences Lab in MIT, working together with Robert Elling and Robert King, using their program. It was a lot of work, but now, with a simple computer, some guy, maybe from high school, can do the same work. Can do the same work and obtain the same vector velocities, the same plate tectonic models, using the capacity of the computers and using only the physics and the science. Then it's true that people say, using these these facilities, the internet, the Google, it is possible to make research and also more possible to do education and research together. It's the most important for me. Imagine something to say. Maybe we need more computer capacity, but not only for simulation. We need computer facilities to validate this simulation. Then we need more earth sciences observatories in order to make validation of the models. We need more temperature measures, we need more sea level measurements, we need more earthquakes validation, more simulation in order to prepare for the simulation of Bernard Mister, etc. It doesn't matter, make a lot of simulation. It doesn't matter. Anybody can do that. It's easy, really. The important is validate this simulation. Then I hope that you say that using scarce, pocos, little funds is possible to make real science. But in order to increase our capabilities, in order to help really to the people, really to the human in the earth science community, we need more measurements in order to validate. Thank you very much. ¿Alguna pregunta, son question?
Okay. Do this all the way. That work? No? There we go. Yeah, duplicate. Okay, great. There we go. Okay, great. Thank you. So you've heard a bit about Caltech collaborating with CICESE for the seismic network questions, and I just wanted to briefly present some cross-border collaborations that we're involved with at Caltech, some of which I think can be helped a lot by the AmLite network, and some of which are going to require additional resources of various sorts. So the first thing I'd like to point out is that at Caltech, we're involved with the Southern California Earthquake Center, which is one of the gateways that was briefly mentioned this morning. A lot of earth scientists use this to go look at, we have yearly meetings, we have a bunch of projects that are funded through this Southern California Earthquake Center to study things relative to earthquakes in Southern California, but also overlapping down into Baja California. And as part of this gateway, they operate on an as-needed basis resources for rapid response to events, including, for example, when we had the April 4th, 2010 earthquake, the El Mayor Cucaba earthquake that you heard about that affected Mexicali, they put up a wiki page so that all of the interested people, we had to be registered participants, but then we could go and exchange information on what resources we had, what still needed to be done, who was going to the field, who was collecting data, with which kinds of instruments. And as always happens in this kind of situation, there's a lot of data that needs to be collected, and there's a lot of sort of rapid things that need to be organized. And this helped us really well for that particular event. The things that ended up limiting us were practical matters such as importation restrictions on getting different kinds of equipment across the border, or just data sets that people had that they couldn't release to us or that required negotiation, particularly things that were privately owned. Another gateway or thing you could think of as a gateway that people use a lot in Southern California and I think also in Northern Baja California is this website that's run by the U.S. Geological Survey. It's called Did You Feel It? And if you feel an earthquake, you're supposed to go and log into this website, assuming, of course, that you still have electricity and internet connectivity, and describe how the shaking felt at your location. And then this information gets combined with all the other observations to make a shake map, which represents how the shaking was felt in different places. Now, in addition to that, we have instruments, the accelerographs that were mentioned as part of the seismic network,
that automatically record the shaking, and maps are produced showing how much shaking occurred in different places. And that is used as for emergency responders to know, and for like the utility companies and all the people who have to deal with infrastructure damage to know where to go. So to just outline the current collaborators that Caltech Seismolab has with Mexican institutions, we're involved with collaborations with CICESE, with UNAM, with the Instituto de Geofísica, and also with Servicio Sismológico Nacional, and with Universidad Autónoma de Baja California in Ensenada and Mexicali, and also Universidad de Sonora in Hermosillo. So we're very interested in having good connectivity to all of these places for purposes of collaboration, as well as to other places in Mexico that other colleagues may be working there, but we're not collaborating there. So to explain a bit about the California Integrated Seismic Network, it contains, as of the last time I checked, like 2 days ago, it was reporting 628 stations. The red ones are the ones operated by Caltech, and the blue ones are operated by other operators, but their data feed into Caltech. So for example, the stations in Baja California that CICESE operates feed into the data stream for this network. And this network is actually funded by, on the US side, by like all of these people here. So State Geological Survey, Federal, Caltech, this is UC Berkeley, and then these people in the middle are California Offices of Emergency Services. So it's another state organization. And the products that come out from this seismic network include rapid locations of earthquakes, shake maps, which are the observed ground motions based on the instrumental records from the seismometers and the strong motion measurements, the accelerographs, and also predicted shaking, because we don't have those measurements everywhere, but it interpolates to try to predict what would have happened. There's software for rapid distribution of earthquake information to the emergency managers who are not scientists, but they need to know where do they have to go fix things, or where are they going to have people who got injured because buildings got damaged, right? The strong motion records, which are maintained as a database for engineers to look at how the buildings responded, and then the seismological data for all the recorded earthquakes, which we archive at Caltech at the data center. And they're currently beta testing an earthquake early warning system, which is in some ways similar to the one that Mexico City has, but we're not going to be doing alarms in the streets. We're just going to be doing warnings to people who, it's mostly sort of emergency response groups, either police, fire, medical, or utility companies. That warns them when the shaking is, after the earthquake starts, the fiber optic signal sends them in advance of the arrival of the heavy shaking, the fact that they're going to get shaken, and they have like so many seconds to respond. And so that's the latest thing we're doing in terms of trying to prepare people and minimize damage. And certainly having the direct connection with the seismometers in Mexico is important for events near the border, because it will allow us to transmit this information better and have more accurate information being sent. So just an example of a shake map. This is a shake map for one of the aftershocks from the El Maricucapa earthquake, and this was an aftershock that was north of the border. These colors show how much shaking was expected in the different places. These are called instrumental intensities, and so a shaking number of 6 is a modified Mercalli 6. Is light shaking, not too much gets damaged, but everyone feels it. So this is sort of the limit of where people start to get really nervous. And this was a magnitude 5.7, so it didn't shake, it was felt over a big area. It was probably felt in Mexicali, but it didn't really damage too much stuff because this particular location isn't an area that has a lot of infrastructure. But you could have an earthquake this big or bigger easily, much closer to Mexicali, much closer to the big population centers. I mean, we have had them in the past where they've ruptured faults that go right across the border here in Mexicali. And so having a good connectivity of all the instruments to be able to get these data quickly and process them rapidly and warn people within seconds of what happened or what might be going to happen is really good. And similarly, for the interests of people in Mexico, if we have a big event up here on the San Andreas Fault, there will be some seconds of warning for the people who are down south of the border, but only if we have the right connections in place to be able to hand them that information. Right now, we transmit seismic data in both directions across the border. The big data packages that come into Caltech are coming from Mexico City, and they're going both ways. We're transmitting from a bunch of seismometers in Mexico to their data center, and then these go up to Caltech, the Southern California Data Center, and then the seismometers in California get all their data get transmitted to here, and that gets passed over to the Mexican networks. And so the research and societal goals from this are that we want better locations of these earthquakes near the border. We want to have duplicate archiving of data for regional earthquakes, especially in case of disaster where one network goes partially down or something. We want to understand the geometry of the sources of the earthquakes. Every day, the data volume that goes back and forth is about 2.6 gigabytes in either direction. And right now, going to Caltech, it takes at least an hour, sometimes more than 3 hours, to get this data up from Mexico City to Caltech. Now, obviously, this must not be going over the AmLight network, is my guess, because it shouldn't be this slow, right? I don't know. But anyway, if that could be faster, that would be good. And the thing is, when the networks get upgraded and we have more seismometers out there, we're expecting this data volume to be 5 gigabytes a day, going back and forth. So we want to be prepared for that. We want to be able to not have it be interrupted or, have it messed up. Okay, another type of collaboration is that after that earthquake in 2010, we deployed temporary seismometers. Octavio Lázaro, who's here, he's at UABC Mexicali. He deployed these seismometers around Mexicali Valley. These seismometers are web-enabled, which means if you can connect them to the web and the web is working, they instantly make themselves into sort of a little fake web page that you could access the data from anywhere on the internet and download this information. And it's very helpful to you if you're studying the aftershock patterns, you want to know what's going on with the seismicity. All of a sudden you have these extra seismometers that aren't part of the permanent network, but they're out there collecting data. So these don't have a really high data volume. They write to a compact flash card, which is like a 4 gigabyte compact flash card. They'll hold data for a couple weeks depending on how you program them, but the problem is we'd really like to get that data right away. And the difficulty we had after the El Maricopa earthquake is that they couldn't get connected to the network. So there's a combination of the way the network drops were configured and the fact that the internet, I think, had local difficulties. And so thinking ahead, if there's anything you could do to improve redundancy and be aware, I guess, that earthquakes are likely to keep happening in this area and they're likely to disrupt infrastructure, and planning ahead in a way to get around that would be great. So let's see, I went backwards, sorry. Okay, the third kind of collaboration is, if you remember in the morning when Minster was showing you the simulation for the shaking and it stopped at the border and people said, well, why does it stop at the border? Remember that picture? Well, he was saying it was because we didn't have a good enough model of the seismic velocity south of the border. And that's true in the sense that there's a more detailed model north of the border, but we have been trying to work on this. And one of our seismology collaborations with CICESE and with UABC Mexicali was a project called the Salt and Seismic Imaging Project that was in the Mexicali and Imperial Valleys. This project set off explosions in 126 boreholes. We had 2,700 seismometers that were deployed and redeployed during the day over a period of 3 weeks to collect data at about 4,000 seismometer locations. And the useful data set that was developed from this experiment is like 1 terabyte worth of data, plus a bunch of other data that we haven't yet used, but that might be relevant to other people. So multiply that by 10, I don't know, or 20. But the idea here is that we need better ways to work with each other when we're working with this data, because the way we transmitted the data to CICESE was by, FTPing pieces of it or, transmitting stuff on hard disks so that they would have it. And CICESE also put out their own sensors during this experiment, so they've been able to get some really good information in terms of fault geometry and basin geometry. The current model for collaboration of this, when we started this project, I actually had to build a wiki for it, for the keeping track of everything that was, we had different field teams going out and scouting out sites for the explosions and the seismometers, and we did that for planning, and it evolved to now interchange of data, but it's not really a work environment. So it sounds to me like we need, NanoWeb or something to take this one step further, and that was great. So I was really excited to hear about that this morning. The Salt and Seismic Imaging Project, if you look at this map, there's the border. We put out seismometers at all these black dots, and we set up explosions at all dots. There were also sources going off in the Salton Sea, and the line down in Mexico was down here, and then like this, and plus the other seismometers that aren't shown that were run by the Mexican network and local deployments from CICESE. So just because we actually do collect data, here's some pictures, like we get outside, we dig holes. Here's a drill rig, it drilled a hole, you know, they loaded explosives in the hole. This is our warehouse full of seismometers. This is why we ended up with a terabyte of data, was because we had put out, you know, 2,700 seismometers multiple times in multiple locations. Another kind of data set that I also want to mention is swath bathymetry data, which isn't seismic data. It's a different kind of geological data. It comes from measuring bathymetry with ships. So your ship has this transducer array either built into the hull of the ship or in a separately towed instrument. It does echo sounding to look at the bottom of the seafloor. You can do a swath like this. And these data actually, depending on how you set the instrument, these end up being, you know, for 1 hour of data, it can be many tens of megabytes, and then you're surveying for hours or days on end. So you end up building a big data set, but it tells you the shape of the seafloor. Here's an example of a map that incorporates that kind of data, as well as other echo sounding data, to get a map of the southern Gulf of California. Here's the tip of Baja California, and here's the mainland Mexico. You can see these lineations in the bathymetry that are on the East Pacific Rise. This is coming from the plate motion that was mentioned before between the Pacific Plate and the North America Plate. There's seafloor spreading here, and it's volcanism, and it's forming these ridges and fault blocks of ocean floor. So when, you know, our current situation with this data set was that if we want to collaborate with someone like at CICESE or UABC Ensenada, looking at these data, we end up working with very small pieces of it because we can't handle working on it in real time with each other, nor can we handle looking at large amounts of it at once. And it would be really good if we had a collaboration tool that would involve us being able to process it simultaneously, sitting in the US and sitting in Mexico, and looking at large data sets, having somewhere where the data can be processed and transmitted, you know, like in real time, not during the cruise. This would be after the cruise is over, but it would still allow us to do much more fruitful collaboration. Anyway, this is just to explain to you sort of the sizes of the files that we're talking about, and hopefully there's something that someone could come up with that would enable that. So here's my wish list for things that might help us. First of all, I think a fast, redundant connections, meaning internet connections, between the seismic data centers would be really helpful, including branching out to all the universities where we want to have fast connections with. For geology, people mentioned this morning these massive online courses, and people in the US are interested in producing massive online courses. There's some test cases going on at Caltech where they're developing a few courses where the public can come in and listen to the lectures online and take these courses and do the work. And the problem we run into in geology is that we have to do a lot of observation, and we take people on field trips. Going to the field is really essential in geology. You can't do it all if you're just staring at a flat screen. And so if there's a way to improve our capability of doing virtual geology field trips, including 3D capability, that would be superb. I think that's, you know, where we need to work with developers beyond what the network capabilities do right now, but that there could be tremendous potential there. Not only for example, having students north of the border be on field trips south of the border and vice versa, but also because you could accommodate a lot more people. Right now, student groups come to do tours of the Seismo Lab, and we can't accommodate more than like 25 of them at once. And so we can't even give tours to a lot of people in the United States who would want to come, because either they can't afford, their school can't afford a bus to get there, or they have 150 people who all have to come, and we can't run 6 sessions simultaneously. So I would think that trying to investigate this sort of thing could be helpful. Another thing I've personally run into that I would like to see somehow improved is the capability for conferencing, so that, for example, when I'm on a student thesis committee, I mean, I can come down to CICESE and I love participating, but if I'm on a committee and it's at UNAM in Mexico City, it would be great if there were a way that worked better than Skype for actually having a conference where you can talk to people back and forth and see what the data that's being presented and even work on it. And so I think as to build upon the AmLite, to make it more useful for people, any kind of improvements in conferencing facilities would be tremendous, and everyone would take advantage of it, and it would be really good. And then the other thing, of course, you run into is the need to use mobile devices. For example, those seismometers I was mentioning that are temporarily deployed, that, you know, the more we can sort of include access to mobile devices, the better off we're going to be too. So that's probably enough, huh? Thank you for your time. And any questions, I don't know. Yeah, I've looked at, well, I haven't really looked at gaming. I've looked at Minecraft. And it may be that we need to do more of that. But I guess what I was thinking was when you go to the field, you know, you see things and someone's going to ask you a question. It's like, what is this? You want to hammer on the rock and like open it up and take a look inside. And so people actually need to be there. And I guess the question is, if you do something like Minecraft, you can't always do everything you have to think it a bit all ahead of time, right? So the question would be if you can actually be in the field doing things and having interaction. I mean, I love teaching field courses, so I'm happy to just keep going to the field and work with students, but I think we don't reach nearly the population that we could reach if we had a better way to do it. Yeah, maybe. Maybe, and then if people were connected, they could call in and ask questions, and yeah. Thank you. Octavio's next, right? Yeah.
Good afternoon. My name is Octubre Lázaro. I am in the Laboratorio de Sismología y Geofísica Aplicada at the Engineering Institute in the University of Baja California. I will talk about the possible collaboration with institution of the United States. We are collaborating now with the Ohio State University and California Institute of Technology. This is our building at the Mexicali after the earthquake of April 4 in 2010, a month after the earthquake. This is my office, and after the quake, this is the front of the building after the quake. 2 months before, we recently opened the lab, and we make a project to build a easy seismometer, a long period seismometer. After the earthquake, the seismometer goes down to the floor. This is part of the rear of the building after the earthquake. Well, by that time, Caltech lent us 3 seismometers for observe the seismic activity in the Mexicali Valley. These 3 seismometers were very useful for record the aftershocks movements. On the other hand, we have collaborated with the Ohio State University. Our collaboration with that university in that we make has been in the a study of 222 radon emanated for the Mexicali soil. We have observed values about 1,000 picocuries over liter. The Environmental Protection Agency of the United States in their writings tells that emanation of 4 picocuries over liter is very, very damaged for the health. And we have observed at the Mexicali Valley values about 1,000 of picocuries over liter. Recently, one of our students make very detailed studies about the urban area and the Mexicali, and this is the study area that student surveyed. Our results are showing that we have a distribution of the values of the emission of radon. So the green label is related to the very low values, about 4.3 to 39 picocuries over liter. And we have in the white label, the values relate about 295 to 320. And this map show some trends. Some of them are related with geological faults. But this is one of the sides of this phenomena. The other side is that many of the places where the levels of radon are very high are related to lung cancer. On the other hand, our collaboration has been made with the California State University, California Institute of Technology, Virginia Tech, CISESE, and USA. We collaborate with that groups to make the study of the crustal structure that Joanne Stock mentioned a moment ago. Another thing that we are making is building seismometer for academic use, and we try to make some innovations trying to update many of the systems that we get, and our job is now try to update that system. We recently win contest about the innovation of systems. This is a record of the one earthquake in March 21 and 2011. This is the records of the USGS. This is the record of the USGS, and this is our records. These are our records. Besides, we are collaborating with the Instituto de Ingeniería of the National University in Mexico, and we have designed with materials of second hand some shaking table to simulate earthquakes and the response of structures in some models. What is the interest of our group in the possibility of collaborate with big data and big network? We think that many of our observations are very weak, but we are trying to get more equipment for monitoring many of the phenomena related with the geological faults. This picture show you the very site with the difference of the 6 months. In the first slide, we are here with some students that were visiting this site, and after 6 months, the same place were moved with the sliding of the imperial fault. This is the same structure. 6 months of difference. Okay, we have only 3 years of operating as lab, and we think that we can help with another institution, and we need your help to discuss what really matters to collaborate, and we are in a position to contribute. Thank you very much. Any question? No question? Okay, thank you very much.
Okay, so good afternoon. I'm Lauren Hare from Pacific Interface. I'm here representing Synagrid. And Cinegrid is a nonprofit international membership organization, a community of networked collaborators working with high-quality media over high-speed networks. We currently do not have any collaborators in Mexico, but we would like to invite people from Mexico to join. The story of Cinegrid really starts here. 1981, this is the director, Francis Ford Coppola, with Dr. Takashi Fujio from NHK Labs at the time, having the first look at HDTV electronic cinema. And Mr. Coppola said, well, I could make a movie with this. And of course, it took a long time. In fact, 20 years later, in 2001, was the first times we started to see what we now call digital cinema. That is distribution and projection of movies in theaters electronically. This is the world's first 4K digital cinema system. These are prototypes, of course. Let's see, this is, here's a PC, actually Linux machine with compressed files on it. It passes through a 1 gig E network. Here's the switch. This was the decoder at the time. This is now much smaller. This many wires went to the projector control unit, which went to the projector. This is a JVC DILA projector. This was a 4K or 2,000 scan lines by 2,000 pixel liquid crystal display manufactured by Sharp. At the same time this was happening, though, there was another vision of the future that didn't depend upon cinema, and this was the Octubre project. In 2004, had a vision of gigapixel wallpaper, which pretty much we're getting close to. 4K streaming video, which I'm going to talk about, we're already there. And augmented reality with no glasses, still not solved. But this was a gigapixel, is basically a terabit per second. Now, Cinegrid projects run over the Global Lambda Integrated Facility. As most of you already know, a network of networks. We run on these circuits through the cooperation of our members. This is the Cinegrid map at the end of last year. These are our major exchange points: Sao Paulo, Amsterdam, Chicago, Seattle, Los Angeles, Tokyo. And you see our members connected there. At Tom DeFonte's leadership, we have tried to develop persistent VLANs that connect members. And just in the last couple of weeks, we had one where we had some persistent VLANs that ran from San Diego to San Francisco, and another one that ran from Los Angeles to San Diego, and tied them together so the people in Los Angeles could talk to the people in San Francisco without making a new VLAN. So this technique works. It is still manual. The VLANs are tacked up by engineers on a one-by-one basis, and they're cross-connected on a one-by-one basis. It is not a scalable system, although it does work. Now, we have a motto in Cinegrid, learning by doing. We have found that there's no place to go to study what we're doing. What we're doing is integration. We're integrating media systems, both sound and picture, with network systems, with compute systems, with display systems, with auditorium, with talent, with showmanship. And we haven't found anyone who knows all of these things really well. So we also need to integrate teams, and we tend to work internationally, so we have to work across time zones and across languages. And this is a very good way to learn. It is difficult every time. These are just some examples. Our colleague Richard Weinberg at University of Southern California has figured out a way how to put a 4K video camera on top of his optical microscope and stream that to remote locations. Our colleague Jeff Weekly at the Naval Postgraduate School in Monterey, California, did dual 4K. He was doing remote sensing of, in this case, he wanted to do it underwater, but we couldn't afford to put the equipment underwater, so he went to the aquarium in Monterey and shot through a glass tank. But technically, it was still difficult. 2 4K cameras streaming over a network synchronized so that it looks as if it's one frame. Our colleague Kunitake Kaneko and a bunch of others from Keio University in Japan went to China and did a live stream of the solar eclipse. That was great fun to watch. Our friends in Prague at Cessnet and Barrandov Studios did uncompressed 4K interactive cinema color grading, sending 4K uncompressed, in this case was 6 gigabit. Now, we have done a number of such demonstrations, and I'm going to elaborate on just a few. This one was between Skywalker Sound, which is north of San Francisco, that's part of Lucasfilm, which is now part of Disney, and the Sonic Arts research team at Cal IT2 in San Diego. They did telecollaboration between these people who are sound editors in north of San Francisco and this man who was a video editor in San Diego. In order to do sound editing, the way it's normally done is you sit in the same room. You're both watching the same, or you're all, sometimes more than 2, watching the same picture and listening to the same sound. All right? And you say, where should I make that bang sound? And you want to say, right there. And you stop the picture and you punch in your numbers and there's the bang sound. Well, in order for that to work remotely, the sense of then has to be the same in both places. So this team worked very hard to get accurate measurement of latency and accurate synchronization. And in media, latency and synchronization are very, very important. In some sciences as well, but in media, it's paramount. And so they had the sound hitting these people's ears, and the sound hitting this person's ears was the same time within plus or minus 1 audio sample, which is 1/48,000th of a second. So very good. And to be able to hold it during the demonstration, which lasted more than an hour, that was really excellent. That demonstration led to this demonstration in 2010 at the Disney Studios in Burbank, California. We did telecollaboration for many cinema post-production tasks, all in the same room. We converted a screening room, not so different from this auditorium, into a place for interactive collaboration. That means we had to bring in networks, but we also had to bring in all sorts of cabling and displays, video conferencing, microphones, echo cancellation, and other things. This demonstration involves Disney, Skywalker Sound, Digital Domain, which is a very large visual effects company in Los Angeles, Laser Pacific, which did the color correction, NTT Labs, which provided codecs and other technologies, Tom's lab, Jason Lee's lab, where they developed Sage in Chicago, and my company. Now, we don't always work with Hollywood studios. We do a lot of work with students. One of the goals of Cinegrid is to help train the next generation of media professionals. And a group of students at Keio University Graduate School in Tokyo decided to make something called the Growing Documentary. And the first iteration was dealt with the tsunami and earthquake of March 2011, which had such destruction in Japan. But the second one, we liked what they did the first time. We said, let's do another one and let's focus on remote collaboration for making movies, or in this case, a documentary made by students. So here's a student team in Tokyo, and here's the student team in San Diego. They never physically met. Every aspect of this project was done remotely, from the discussion of the concept to the storyboarding, the writing, the editing, the post-production, the audio mixing, and finally the presentation. And we learned a great deal from it. This is another view of the same project. This is Todd Margolis at UC San Diego presenting about it. And so what we basically did is we explored network-supported collaboration process for making media. If I can make media over networks, I probably can do scientific visualization over networks. Combine traditional production tools with new tools. vRoom, that's this whole infrastructure here. CineSage, which was a modification of the Sage tile displays. Pix, which is a collaboration application that's commercially available. We used a cloud server for media transfer and storage. We used multi-channel 4K and HD video conferencing for face-to-face discussion. Very helpful. Especially, a lot of people do video conferencing in the television business now, but they have to rent satellite circuits. This community is used to doing video conferencing via Skype, which is free and not very good quality. I use it myself all the time. It's free. That's the best benefit of Skype. And did I say it was free? All right, well, if you want higher quality, it's not free anymore. And if you want multi-locations, it's not free anymore, especially at high quality. So we find that having the video conference system always active is really conducive to having a good collaboration. So it doesn't have to be scheduled. Now, we have done a number of experiments. This one was by the Netherlands Film Academy, based in Amsterdam, and SARA, the Dutch Supercomputing Center, that was presented at the Cinegrid workshop in December of last year. So a live action camera, actors and green screen stage were in Amsterdam. The virtual set compositing was done at SARA in a different location in Amsterdam, and the remote viewing and the director was done in San Diego. Here's the diagram. So first location in Amsterdam, here's the camera, the microphone, stage cameras, the screen, the green screen, and so forth, and the video conferencing system. The output of this camera, together with all of its metadata, so we use something called Lightcraft, which captures camera telemetry. So it knows where is the camera in 3 space, which way is it pointing, what is the lens zoom, what is the lens iris, and when do you press record. And you send all of that, plus the picture, pardon me, to the supercomputing center, which has a virtual model of a room. And they do live compositing, combine the 2 images, and send the result to San Diego, where the director is watching it and giving instructions. Here it is as it went down.
Iedereen klaar? Ja, Robin. Oh yeah, yep. Okay.
Sorry? This is what we're looking at.
Action.
These people are in Amsterdam. This is what the camera in Amsterdam is seeing.
Okay, thank you. Can we go back and then do the same scene but then with the virtual set this time?
We gaan nu iets verder, Harry.
Okay.
We gaan nu door de deur heen.
Yeah. Yeah. So what we do now is the virtual set. With it combining with the real set. What I want to show with this track is what you can suggest in inside and outside world.
Wij zijn klaar, Harry.
Yeah?
Yeah.
Okay, ready? Robin, can you remove your head, please, a little bit? Okay, thank you. And action.
So here's the live composite. So now there's an outdoors, and you'll see as she walks into the So the only thing that's real are the doors. This is all into a virtual set now, composited on the fly. You're laughing because your hands don't quite meet the railing. Right, so when I show this to my friends in Hollywood, they say, wow, nobody would ever go to such an effort. Why, we do this all the time in the same studio, but why would you separate it? Well, on the one hand, the Netherlands Film Academy is teaching their students what the future might be, not what today is. Prepare them for tomorrow. And secondly, there are cases where, especially a well-known director can't be everywhere they're supposed to be. Right? Larry Smarr could not be here today because he had to be in San Diego. So we had video conferencing. All he had to do was PowerPoints. What if he were a film director and he had the same problem, which happens? So this is a thing that might happen in the future. It's not practical today. It's technically feasible, but not commercially viable. But that's okay for Cinegrid because we're supposed to experiment. So Cinegrid has taken a scale approach. Now I'm going to talk a little bit about numbers. So on the right here are the different grades of imagery that we can find in the world today. And over here are two sets of numbers. The one on the left is the distribution bandwidth, the bit rate for distribution. And on the right is the recording bandwidth, that is what we normally would call the baseband, or the original. Right, so let's see here. So if I watch HDTV television in the United States, and I watch it over cable or satellite, this is probably the compressed bit rate. If I watch it over the air, digital terrestrial, it's 19.3 megabits per second. If I go to Japan, it's 20.7 megabits per second. But if I record it and send it through a cable, every time it's 1.5 gigabit per second. That's the uncompressed bit rate of HDTV with 8 channels of uncompressed audio in synchronization. Well, I can make stereo HD. Now, it turns out that 20 megabits, which you'll see repeated here, is essentially 6 megahertz of RF spectrum. So television runs through the ether. We do emission through using radio frequencies, modulated radio frequency. And each channel, not by tradition, but by history, and at least in the United States, I'm not familiar with Mexico, but in the United States, by regulation, is 6 megahertz. I have 6 megahertz, then there's a guard band, then the next person has 6 megahertz, and so forth. And this RF spectrum is licensed. You don't get it, well, you get it for free, but you only get it what you're assigned. And you can drive 20 megabits through that, essentially. And so the distribution bandwidth for HDTV in stereo is roughly 20 megabits. That's the maximum. All right. Now, baseband is twice because I have left eye and right eye, 3 gigabit. Digital cinema, which is not streamed in real time, is by agreement with the Hollywood studios, is sent as a non-real-time file transfer, has a maximum distribution bit rate by standard of 250 megabit per second. But the baseband of 4K at 24 bits here, 24 frames per second, pardon me, is 7.6 gigabit. Because cinema runs at higher bit depth, that is more dynamic range than television. Well, we have something new called UHD, or UHD TV. There's 2 versions, UHD 1 and UHD TV 2. This is comparable to 4K. This one's comparable to 8K. We're measuring pixels on the horizontal dimension. Well, UHD has according to the standard ratified in January, has a frame rate potentially of 24, 30, 60, actually there's a 50 I didn't write down because I'm an American, and 120 frames per second. That's, if I want to send it over digital terrestrial television using the towers that exist today, I have to squeeze it to 20 megabits for distribution, but the baseband at 120 frames per second is 48 gigabits. Right? Now, UHD2, I could send stereo. Well, I'm just going to double it on the baseband, but I'm going to have to squeeze it more because I still only have 6 megahertz. And if I go to 8K, which has maximum 120 frames per second, my distribution bandwidth is still the same, but my baseband's 192 gigabits per second out of the camera. Oh, and sorry. And if I'm Tom DeFonte and I want to make tile displays and camera arrays, I don't know how high he's going to go, right? Because there's no limit. You just keep adding them as modules. So here's a more detail for those of you who like to see the numbers. So horizontal pixels, vertical pixels, frames per second. This is just what I talked about. And what you see is 30, 25, 24 frames per second at this kind of sampling, which is common in television today for production. By the time it reaches you at home, it's much less, is 6 gigabit per second. I can send it down to a single 10 gig E link. And Cinegrid has been doing this because that's the best we can do is 10 gig. But if I go to higher sampling rates, and those of you who want to know about this nomenclature, I'll explain it later, that's all of a sudden 12 gigabit. And if I go into this far right, 120 frames per second at the maximum sampling, 48 gigabits per second. If I go to UHD TV 2, which is the same as so-called 8K, which Japanese broadcaster NHK has been promoting, it's 4 times the data rate of this that I'm showing you here. All right, so the 6 becomes 24, the 48 becomes 192. There is no single cable real-time interface defined yet for these systems. So the only way we can move it around in real time is by parallel transmission. Now, this was me standing in Shinagawa Station in Tokyo last October when Sony just announced its 4K consumer television. This was an 84-inch diagonal LCD for $25,000. They didn't sell very many. That's not the purpose. The purpose was to start the market. Since then, they have come out with somewhat smaller displays that are $6,000, $5,000. There's a company, as Tom mentioned, from China, Seiki, who none of you have ever heard of. I've never heard of them before either. They have a 4K display for less than $1,000. The point here is that 4K is no longer just for cinema. That's where it started, but it's no longer just for cinema. It's coming in the form of UHD TV and gaming to the home. So Intel's Haswell chipset with the Iris GPU can output 4K native. The new Mac Pro, which is supposed to be announced later this month, can output 4K native. The Xbox can output 4K. The PlayStation can output 4K. So this stuff is coming into your home. Well, why is more resolution better if I'm in the entertainment business? Because it certainly costs more in terms of bandwidth and storage, right? And the reason is this, that more resolution allows closer viewing of a larger image. And closer viewing of a larger image increases the viewing angle, and increasing the viewing angle produces a stronger emotional response. If I'm telling a story, what I'm really trying to do is create an emotional response. So increasing the viewing angle creates a stronger emotional response. And here we have it. Here's HDTV. This is its horizontal resolution, its vertical resolution, and its optimum viewing distance is 3 times the picture height. You get a 30-degree viewing angle. If you go to UHD1, 3840 by 2160, optimum viewing distance is 1.5 picture heights, 60 degree. That means you can sit as close as 1.5 times the picture height and not see the pixel structure in the picture. It still looks smooth to your eye. UHD-T2, also known as 8K, twice horizontal, twice vertical, and that gives you 3/4 of a picture height, 100-degree field of view. This is what you get in an IMAX theater. And any of you who have been to an IMAX theater know that it can really impact you. Now, done improperly, it can make you nauseous. It's how strong the impact is. Done properly, you think you went into a virtual reality, even though it's still just a flat screen. Now, the concept of Cinegrid is that we are trying to promote exchange of ideas and technologies between three fields in society. The three fields that have always, for hundreds of years, always driven the state-of-the-art of media technology are always the same. There's art, entertainment, culture field. There's the science, medicine, R&D activities of a society. And there's the military, intelligence, police activities of a society. These are the parts of society that either because it's their mission, or it's their passion, or it's their responsibility, always want the best media they can get and somehow manage to get the budget to get that media, or they have to invent it themselves in some cases. So I've talked for a few minutes already about broadcast and cinema, but I have my spokesperson here who's extremely articulate. He's going to explain why it's important for science.
I'll just give you one example of many kinds of repositories of the data, this being the protein data bank, which...
And so what I want to show you here is not Larry Sparr explaining about how come science is important or big networks, but rather that Larry is standing in front of a 64 megapixel display, and that each one of these tiles is HDTV, that's 2 megapixels. So in the future, Tom hopes actually by December, if everything goes well, to be able to show the same idea of tile displays using 4K tiles instead of HD tiles. Eventually, the tiles could potentially become 8K, each tile. Same middleware, same computers, higher bandwidth, which is a challenge. Right? And this diagram, I think Tom showed in his presentation. But this is what happens when you can get really large images. They have a dramatic impact. Now, Larry is lecturing to an audience here, and he's a terrific presenter. So, you know, he could have done it with shadow puppets. But for the rest of us, the ability to have very high quality imagery running over high-speed networks is good for science and good for science education. So this is another approach, not flat screen, but rather immersive circular screen. Many of you know about the cave that was developed by Tom and his colleague Dan Sandine in Chicago in 1990 or 1992. And that was a room, or part of a room, typically a cube shaped, with rear projection on each screen. That works really well, but you need a very large room for the projectors, and then inside is a small room where you actually see the images. And it's fairly dark, and you can't fit very many people. So Jason Lee and his team at the University of Illinois in Chicago at EVL have developed the Cave 2. 72 megapixels, all 3D stereo, all with motion tracking, 20 channels of audio, because it turns out that immersive experience of media, audio and video work together, and 100 gigabit networks to Starlink. Here's an example of what can be done in such a space. This is by a grad student. So he went out and he got the CAD/CAM database for the Starship Enterprise, and he built a virtual set. At Lucasfilm saw this, their first response was, let's hire him. You know, the good news is he decided to continue for his PhD. And then they'll hire them. So this is just an example of what can be done. It's worth seeing if you ever get a chance to go to Chicago. And there's a new one now being built at Monash University in Australia, just built, I think, last week. So it's a new way of looking at science and looking at architecture, even looking at archaeological data or seismic data. The petroleum exploration industry uses this kind of technology already very extensively. It works for medical training, surgical training. Now, I didn't have this in my presentation when I sat down this morning, but listening to the earlier presentations before lunch about worldwide data sharing and collection of scientific data sets, I asked a question of the speaker who was at UCSD, how are you saving your data? Who's saving it? How long are you saving it for? And his answer was, oh, I send it to a nationally funded data center. And it's like, you know, I flush my toilet and it goes into the sewer. What happens next? What happens after that? Why are you confident that the data center knows what they're doing? Because I can tell you, because I've been studying this topic for now almost 10 years, nobody has an answer to long-term preservation of digital data. Nobody. The answer that we have now is called migration. You record it onto LTO1 tape. 3 to 5 years later, you record it onto LTO3 tape. And 3 to 5 years later that, you record it onto LTO5 tape. And 3 to 5 years later than that, you're going to record it onto LTO7, which is not yet developed. Now, oh, I don't use tape, I use disk. Okay, we're going to record from this disk to this disk to this disk. And for 40 years, the price per bit of data storage has been falling at 40% per year. If you plot it on a log chart, it's a straight line graph that asymptotically approaches zero. So that says transferring my old data from my old media to my new media, I'm going to fit my old data into this new thing, and it's going to be smaller, it's going to be faster, might even be cheaper, right? That's great. Of course, there's this cost of transferring it every 5 years that nobody has worked into their business models. A very few have worked into it. San Diego Supercomputing Center recognized this fairly early on because they had large data storage, and it was costing a lot of money that nobody was paying for, so they had to put a cost to it. They did the analysis, and what they found is that the cost of the media is increasingly or decreasing in importance. The cost of the electricity to power the devices and to cool them, the cost of the real estate, and the cost of the software licenses for file systems, and the cost of the staff to run it, those are only going up. And no end in sight. As fast as, so I said that the areal density of storage is falling at 40% per year, but the production of data is rising greater than 40% a year. So we're accumulating more and more data. We have no reliable solution for preserving it. And I will tell you that in one of the marks of a civilization is that it takes the output of its generation and passes it to the next generation. And the next generation builds on it and passes it to the next generation. And as we enter the information age or the digital society, if we cannot pass on to our next generation the output of this generation's work, it's going to be a really fundamental change in how human societies evolve. Not genetically evolve, but as societies, as organizations. So I have been working in Hollywood, not in science, and so I'm looking at what happens in media technology. And this is from a presentation by Andy Sitos and Jim DeFilippis, who until recently were very senior executives at Fox. And they made a presentation in February of this year, which I'm quoting here. So the conversion from analog to digital formats has fueled an increase in media data. So an HD generates 30 hours of media at 200 megabits a second, 2.7 terabytes. A season is 30, it's usually 26 weeks in America, 60 terabytes. Do it in 3D, it's going to double it. If you do it in 4K, also known as UHD1, it quadruples. I now have a quarter of a petabyte per television show per season. So that could be a reality show, it could be a drama, doesn't really matter. A movie, according to what's called the digital DCI specification, is 1 to 2 petabytes per title. 3D doubles it. If you go to high frame rate, you can triple it. And this this slide is an error where it says 10 to 15 terabytes at the far right. It should be petabytes. And distribution, this is the one that really catches us. Every new online distribution requires their own file format. You want to sell your old TV show on Hulu, they're going to use one file format. You want to put it on Vimeo, different. YouTube, different. Well, YouTube's not a good example because they do the encoding and storing for you. Those of you who don't know and enjoy YouTube, you should look at the Wall Street analysis. The debate is whether Google is losing $400 million a year or $600 million a year operating YouTube. So it's good for their advertising, but they, only Google can afford to lose so much money on something like that. The real thing, though, is that let's say I want to sell my TV show on Apple, iTunes. I have to encode it for Apple. And I'm going to send them a copy, but I'm going to keep a copy for myself. Now I want to send it to Android phones, different encoding. I need to do the same thing again. And what you come up with, according to Mr. Setos and Mr. DeFilippis, who really are knowledgeable, is that assuming that the consumer distribution is 1 to 4 megabits per second, which is what I showed on my little triangle diagram, for a 1,000 hour library, that could be 2 petabytes for each distribution deal that the sales department brings in. Sales department brings in, good news, I landed a deal, I sold 1,000 hours out of our library. I want my commission, and he'll be paid, as he should be. Then the operations guys make these files and say, I did it, all done. And they turn it over to the archive department, and the archive department has a big problem. And this is a problem, I believe, that we're seeing in Hollywood, we're seeing it in broadcasters, and we're going to see it in the scientific community. But one of the answers is, for preservation, is that you must geographically distribute your repositories. We've just had all these presentations about earthquakes in this region. If you kept Sassezi's data files here, and you had a big earthquake, and the university fell down the hill, right? What happens to the data? If we have it in Los Angeles, which is on the wrong side, the Pacific side of the San Andreas Fault, we could lose archives. Now, in the scientific world, that's intellectual property, that's data that can't be captured again because it was transitory. It could have been a decade of sensor data. In Hollywood, these movies cost $100, $200 million a piece to make. Those are assets carried on the balance sheets of these corporations, and if you cannot read them, you have to write them off. So you need to distribute your data to multiple, at least 3 geographic locations. You need to not be dependent on a single technology. You need to have something that can be sustained. Archiving starts now and ends never. This is a very different problem than how do I get my website running. Although it suffers from the single greatest risk to digital preservation is the same as your scientific gateways. Loss of funding. When you're archiving analog material, so for many years, cinema has been archived on film. You take color separations, that is, you take your color film, you separate it into red, green, and blue, you write that onto monochromatic film that's got special chemistry using polyesters so that it doesn't move, it's thermally inert. Put those films into a plastic bag, You fill the bag with nitrogen gas, which is also inert. You seal it, and you take that and you put it in a cave underground where the temperature is constant. And it's dark and dry. And you can leave film like that, and 50 years later, come back and watch it. You cannot do that with digital tape or digital disc. Disc will have stiction, tape will have oxide loss. But more important than any of that, just how much data Hollywood's going to generate. They'll be generating exabyte in a few years. This is the real problem, and I believe that this problem is a good example of Cinegrid. This is a problem that affects science, affects military, affects entertainment. This is what you have to deal with if you're going to do it. So, in order to preserve something, I need to navigate. I need my host computer to work, and I need the applications that work. And every 3 to 5 years, that changes. I have physical interfaces, plugs. You know, how many of you still use SCSI, right? Or, you know, name any other plug you want, you know? And the interface firmware for those plugs, they cycle every 5 to 10 years due to commercial pressure and technological advance. The media, that is the tape cartridge or disc, and the file system, file format, and physical recording format, the block structure, that's going to change depending on what you use. CD-ROMs and DVDs change around every 6 months. Into enterprise quality tape storage every 10 years. The personnel, that's going to vary, but you better train the next generation while the current generation is still before they retire, or nobody will know how to open your archive. You know? And your funding. So if you lose funding on a digital archive, and it will last, the archive will survive a number of years, and then it will become unusable. If you lose funding for an analog archive, it can survive benign neglect for 20, 30 years, but not a digital archive. So this is a very new problem. So many people in the entertainment production world, that is the creative side of things, they love digital technology. It gives them faster response time. It gives them lower costs on production. It gives them more creative control. It's all good. Unfortunately, they were not counting the cost at the tail end. So we have to learn to look, both in media and in science, what is the cost up front to gather the data? In my business, that means shoot the picture, record the sound. What does it cost to process it? In your sense, that's the compute clusters and moving the data here and there. In my world, that's the compositing and the editing and the visual effects. And then what does it cost to preserve that data? That's, when I first looked at this topic in 2007 for the Academy of Motion Pictures and Arts and Sciences, I went to a major studio and I asked the person in charge of archives, what is your electricity cost? And he said, I don't know, it's part of my overhead. Well, what's your overhead charge? I don't know, I'm just here in the studio, somebody else takes care of that. And that won't fly as we go to a digital age, just as the speaker from UCSD earlier today who said, oh, I send the data to a national government-funded data center. Not sustainable, unless the government's prepared to put more and more budget into preservation, which probably means less and less budget into compute and networks and storage. This is a challenge that this community pay attention to as well. Cinegrid is an international community of network collaborators. We have an international workshop this year coming up 9th through 11th of December in San Diego at UC San Diego. We try every year to do something new. And as Larry said, and as Tom says repeatedly, we should be aggressive in what we try to do. We prefer collaborations, but not always. We look at technologies, we look at applications, ranging from movie production to museums and educational applications. You would all be welcome to attend. Thank you so much for your attention. I'm happy to take any questions. Heidi. Mm-hmm. Mm-hmm. And it's an entirely viable approach. One of the greatest film archives in America was at Eastman House in Rochester, which was funded by the George Eastman Foundation. The other great archive is the Library of Congress, funded by the tax dollars, right? We have to. I know them, directly, professionally. They're extremely competent and thinking very deeply about this. They recognize they don't have a long-term solution. They are implementing the current best approach. So I do believe that they will be if anyone in our country has thought hard about it, they are. The National Archives and Records Administration, which also has a legislated or operates under law, under congressional law, right? Which is to save, the National Archives is responsible for saving the output of government agencies for the life of the Republic. And they've been working on this problem for more than 10 years. So there are people who work especially in government, who deal with documents, who work in libraries, who have been coming to understand that it's possible to go to a fine arts repository, a fine book repository, put on your white gloves, and look at a Gutenberg Bible printed in the 1300s, or the Manyoshu written in 1200 in Japan. It is not possible to do that with digital content. And so the libraries realize that more and more of their content is coming to them as PDFs and PostScript files. It was never on paper. What if I want to document a government website? It didn't exist on paper, so how do I document it? How do I preserve it? Even though I'm required by law to do that. This is a big challenge. So I do think the Library of Congress has a good handle on a bad situation, and they're doing their best. And they're thinking real deep about it. Tom? And it's a loss. I have my personal work in that library, in that collection, and it's a loss. Yeah, if you right. Right, so one of the topics that's a very hot topic right now in this archiving of media is, should I compress the data or not? Right, and it turns out that I can save mathematically lossless compression between 2 to 1 and 3 to 1 compression. But Compression adds complexity. And now I have to preserve the codec algorithm and the documentation for that so that I know that in 50 years somebody can read it and decompress my content. If your archive's no longer accessible, it's gone. If you lose the metadata, it's gone. You know, and so this is a new phenomena that, you know, we can go back and read Thomas Edison's lab books or Alexander Graham Bell's lab books, you know. I'm sure that you don't keep lab books anymore. Maybe you do, but certainly most people don't. They keep blogs. They keep home pages, you know, which are mutable. They're changeable. There was another question down in the front. Okay, so there is so many different types of metadata in the media business. There is not one standard. There are multiple standards. None of them really satisfactory. They're best efforts. There's been a lot of work. So, for example, the Academy of Motion Pictures developed what's called the Academy Color Encoding Specification, which specifies the metadata and mathematical transformations you do as you change colors, as you move from device to device. It took 3 years of discussions to come up with a draft that the experts could agree on, and then another 3-4 years to be promulgated. And now it's starting to be used. So convincing people to accept the same metadata is very much a matter of persuasion. Now, the common metadata of a video or a cinema would be horizontal pixels, vertical pixels, frame rate. That's very basic. But now I want to know what is the color space that you use, because there are several. And I want to know the color sampling, and I want to know the bit depth, right? And then I want to know, do you want to know what camera it was shot with? Every camera manufacturer generates different metadata in different forms, not consistent at all. So they suffer from very big challenges of interoperability. Everybody complains about it, but so far nobody has a single solution. One of the solutions may be for media to develop what is called non-textual metadata.